What is science? It's a surprisingly hard question to answer. I always think about a mural in the Vatican painted by Raphael in the 16th century. In this painting, we see the Greek philosopher Aristotle holding his hand down to the earth. And next to him stands his teacher Plato, who's pointing his hand up to the sky. Raphael used these subtle gestures to symbolize each philosopher's theory on the source of true knowledge. For Plato, true knowledge came from thinking about the ideal versions of everything we see around us. But for Aristotle, true knowledge came from carefully observing the world as it is, making him the first scientist. It wasn't until 2 millennia later, in 1833, that the historian William Whewell actually coined the term scientist. Before then, people who studied nature were called natural philosophers. And in the centuries between the lives of Aristotle and Whewell, more and more people began studying the natural world's intricacies through careful observation. But science has arguably made even larger leaps in the period since the 19th century. We now know the age and constitution of the universe, the mechanisms of heredity and infectious disease. We can split atoms and we can build machines that write symphonies and beat the best of us at chess. In other words, science has become an enterprise that permeates all corners of humanity for better and for worse. It's led to dramatic improvements in the lives of human beings, but it's also led to much misery and suffering. How has this progress been made? And is this even progress? Is it real or is it an illusion? Our goal will be to take a close look at how scientists today generate knowledge. And along these lines, we'll ask whether their methods are really as reliable and objective as they seem. We'll also discuss whether non-scientific values such as moral codes, religions, or politics should play any role in guiding the scientific enterprise. Science is a word used in the public and political spheres. In her 2016 Democratic National Convention address, then presidential candidate Hillary Clinton said, "I believe in science," which was followed by roaring applause. Then after the election of Donald Trump, hundreds of thousands of people took to the streets all over the world for the Marches for Science. These people all took a strong stance for science, but what does that really mean? What are they marching for? Is it a method, a body of facts, a set of values, a group of individuals? Well, from the birth of careful empirical observation with Aristotle, to the solitary studies of Isaac Newton, to the observation of distant galaxies using the world's largest telescopes, science has constantly evolved and become more complex. Unlike centuries past, today science is a collaborative endeavor taking place in nearly every country across the world, and all of this work costs money, lots of it. In 2017, my home institution, the University of Pennsylvania, alone spent nearly $1 billion on research projects. The majority of that money came from the federal government, who will spend over $175 billion on research and development in 2018. And industry also funds millions of dollars of research at Penn and billions of dollars in the United States overall. So what are the end products of all of this spending? Let's take a look at a couple of recent examples. In 2017, scientists observed the merging of two neutron stars for the first time. According to the journal Science, it was easily the most studied event in the history of astronomy, with 3,674 researchers from 953 institutions collaborating on a single paper summarizing the merger and its aftermath. The first image of the neutron star merger was taken by the SWOPE telescope at the Las Campanas Observatory in Chile that we see in this image. The observation provided evidence to support Albert Einstein's theory of general relativity, a theory that continues to be supported to this day by observations. It also elucidated the process by which heavy metals like mercury and lead are produced in the universe. Last year, scientists also discovered more fossils of our species, fossils that led them to believe Homo sapiens has been walking around on this planet for not just 100,000 years, but 300,000 years. In other primate news, researchers also discovered a new great ape species, an endangered orangutan living in Indonesia. This was their first discovery of a living great ape species in 90 years. In 2018, scientists began the first experiments with humans using a genetic technique called CRISPR-Cas9. Their aim was to modify human immune cells to kill cancer. In that same year, researchers also found that emissions of CFC11 were on the rise again. This had been banned all over the world in 1987 because it puts holes in the ozone layer, which leads to more ultraviolet radiation making it to the surface of the Earth. Researchers have also begun to investigate the many ways that bacteria living in our guts, what scientists call our microbiome, might affect our physical and mental health. Their preliminary studies have shown that there could be some connection between the microbiome and obesity and immune disorders. Researchers also suggest that the microbiome may increase the risk of developing neuropsychiatric illnesses like schizophrenia, obsessive compulsive disorder, ADHD, and chronic fatigue. It's very new work, and many scientists remain very skeptical, but this is normal for such a new research program. Studying the collision of neutron stars, dating our fossil record, measuring air pollutants, using genetic techniques to cure cancer, linking gut bacteria to illnesses, discovering a new orangutan, what do we think all of these disparate activities have in common? How do they fall under the same heading, namely science? Every question I have so far posed is a philosophical question. These are the questions asked by philosophers of science. As we've already learned, science has its origins in philosophy, but today the philosophy of science is a discipline that asks what science is, how it works, and what role it should play in our society. So many of the decisions we make in life rely on scientific evidence, from the chemicals we decide are safe to the way we raise our children, so we better understand why we accept the evidence in the first place. We should ask, is scientific research really the best way to answer the hard questions that society faces? Is it the only way? The philosophical analysis of science can elucidate answers to these questions. Throughout the course, I will refer back to a handful of core examples that illustrate how diverse the scientific enterprise can be. I'll also use these examples to explain the characteristics that unify all scientific activity. So as someone who spends a lot of time in nature, when I think about science, I don't immediately turn to the laboratory or the stars, but what first comes to mind for me are the intricacies of forests, oceans, and deserts. So I'm going to start by describing what's arguably the greatest scientific achievement in biology, evolutionary theory. When you went to work or school this morning, did you take the time to really look around? I live in Philadelphia, and while it doesn't exactly fit the stereotype of an idyllic natural setting, even in the city, every corner is teeming with life. You'd probably walk by some relatively large animals like pigeons and squirrels, maybe even a woodchuck, but if you stop to take a peek under some bushes or behind a dumpster, you'll probably spot some smaller mammals like mice and rats. And throughout the city, there are heaps of insects, including cockroaches and bedbugs, which both seem to survive our greatest attempts at eradication. And you'll also notice that trees have coverings of moss and lichens. In darker corners of the city, we'll probably find spores, molds, and fungus. And if you had a powerful microscope, you'd see that billions of bacteria are in the soil of our parks, our buildings, and trolleys and trains. Bacteria, in fact, are everywhere, on the table you're sitting at, on the computer you're watching this video on your skin, and as you already now know, inside your body. There are a lot of questions we can ask about the diversity of life that permeates both our forests and our cities. How did these species get here in the first place? And despite their diversity, why do they have so much in common? These questions are answered by evolutionary biology. I'm lucky to work in the Galapagos Archipelago, which is located off the coast of mainland Ecuador in South America. This is one of the best places to study the phenomenon of adaptation. These islands were never attached to the mainland. When they first formed from volcanic eruptions millions of years ago, the islands were devoid of life. So every species that now calls them home had to swim, fly, or float there. These living things then adapted to the harsh environment where food and water were and continued to be scarce. The Galapagos giant tortoise, one of the last remaining species of giant tortoises on the planet, possesses one of the most striking adaptations in the island chain. Giant tortoises are land grazers, much like sheep or goats in North America. So their survival in the Galapagos environment depends on their ability to gain access to vegetation. On some of the islands, where lush vegetation is available on or near the ground, tortoises with dome-shaped shells can easily access food. But some of the islands are extremely dry, and vegetation is only available above the ground. On these islands, tortoises' shells take the shape of a horse's saddle and are aptly named saddleback tortoises. This saddle shape allows these tortoises to reach their neck high up to eat the only available vegetation. Biologists would say that the saddleback tortoises are well adapted to life on dry islands, while the dome tortoises are well adapted to life on the lesser islands. This kind of phenomenon, good fit between organisms and their environment, has been known all the way back to Aristotle. But since tortoises can't change their shell shapes, what explains this adaptation? In fact, it was in the Galapagos Archipelago that the naturalist Charles Darwin gathered some of the most important insights into the mechanisms by which populations of organisms adapt to their environments over generations. Darwin called this mechanism natural selection. We could do a whole course on evolution, but in brief, here's how it works. The key is to first take notice of subtle variations over drastic ones. Even though all of these tortoises are dome-shaped, each one is a little different. We can see these differences if we look at the V-shaped area of their shells, the two scales at the spot where the head sticks out. Some of these tortoises have their neck scales pointing forwards or downwards. But other tortoises have these scales pointed a little bit upwards. These individuals can reach their necks just a bit higher than their cousins with neck scales pointing forwards or downwards. When food on the ground is scarce, if a tortoise can reach just a little higher, it can get more food than the others. More food usually means more offspring, and these offspring inherit the upturned shell trait. Then very slowly, over many generations, there will be more and more tortoises with upturned shells on the driest islands. Eventually, after many generations, tortoises that live in these dry environments end up looking like the saddleback tortoises we see today. And it's not just tortoises. Darwin and many biologists that came after him have also studied Galapagos finches to better understand adaptation. Like the tortoises, these 17 species of finch have adapted to life on different islands by specializing in obtaining food in different ways. Some have big beaks that can crack larger nuts, and others have small, narrow beaks, better at handling smaller seeds. But their ancestors were all the same species, a species that likely flew over to the island chain thousands of years ago. So their beak shapes are largely the result of natural selection, helping populations to cope with different sources of food. And again, natural selection worked with small differences in body and beak shape. It's very hard to see these small differences, what biologists call variation, when we're in the field. But generations of scientists have brought samples of finches back to museums like this one so that they could be studied. Most studies of adaptation have to infer how natural selection operated, since we can't go back and replay the past. But there are some important exceptions to this, and one of them happened in Galapagos. There, Peter and Rosemary Grant studied the medium ground finch on Daphne Major Island for 40 years. During that time, they were able to follow each individual bird and its offspring, observing how small differences in beak size made big differences for individual finches in years of drought. They found that in extreme drought, when the only food that was available were hard, woody tribulus seeds, the birds with larger beaks did better and passed this larger beak trait to their offspring. Now you might be wondering, how practical is it to do a study like the one conducted by the Grants, one that lasts over 40 years and involves tagging every single animal in an entire island? The answer, I'm sorry to say, is it's not very practical. It's time-consuming and expensive, and few areas of the world are as suited to such study as Daphne Major. It's a very small and isolated island, even by the standards of the Galapagos. But there are other ways we can study natural selection. We can also study it in the laboratory, which Professor Mia Levine is doing at Penn.
My lab uses the model fruit fly of the genus Drosophila to conduct our evolutionary genetic studies for a variety of reasons. So first, we can do experiments in the lab with this fruit fly. It lives in a tiny vial, it has a very short generation time, and we can pull from the 100 years of genetics that fruit flies have been huge contributors to, and use those tools to ask actually evolutionary questions. There's also the genome sequences of hundreds of Drosophila species that we can leverage to discover those signatures of very recent adaptation or very recent evolution. My lab is very interested in the genes that make proteins that glom on to DNA in our cells. So we focus specifically on the subset of the 14,000 genes that Drosophila melanogaster, the model fruit fly, encodes, specifically looking at those genes that make proteins that do this important function. Once we've identified genes that change very rapidly between closely related species, we use genetic engineering, specifically CRISPR-Cas9 mediated transgenesis, where we put foreign pieces of DNA back into that model fruit fly and ask what happens. So while a true molecular geneticist will knock out a gene or change some portion of that gene and ask what breaks in that organism in order to understand what that gene does, what my lab does instead is we take versions of that gene from closely related species, put it back into Drosophila melanogaster, and ask what breaks. And we think that what breaks when we put the wrong species version of that gene into our model organism, that tells us what's the biology that evolution has shaped in the past 500,000 to 2 million years of evolution. We are specifically interested in genes that encode proteins that glom onto the DNA. These proteins perform really important functions that you think shouldn't change between Drosophila and humans, let alone between two very closely related Drosophila species. One of our projects is understanding specifically why proteins that ensure our chromosome ends maintain their integrity. Why should proteins like that change so rapidly between closely related species? Now, we can't do these gene swaps and simply look at the fly and ask, does its wing change, or does its eye change, or does it move differently? The phenotypes we're interested in are ultimately phenotypes that we need to look inside the nuclei of this organism to detect. And so we do that by not just putting the wrong species version of a gene into Drosophila melanogaster and seeing what breaks, but we actually put a special little tag, as we call it, on the end of the gene that allows us, using antibodies and fluorescence microscopy, to actually visualize where these wrong species versions of those proteins go inside the nucleus of this particular species. We then can infer the type of biology that has changed over these very short stretches of evolutionary time.
We've now talked a lot about adaptation and natural selection, how it can be observed and how it can be studied. We've seen that the study of adaptation often begins in the field with careful observations of organisms in their environment. But when scientists need to get a bit more precise, they can take collections back to the laboratories for more careful measurement and analysis. Laboratory experiments also allow for direct manipulation, giving scientists a greater ability to control certain variables in a system. This allows them to pinpoint the effects of one variable from another. The most reliable information comes from the integration of different research methods. This we will see as a quality that ties all of our core examples of science together. When I'm not wondering about how species became so well adapted to their environments, I like to think about how and when the universe as a whole came into existence. And in this domain, it's not Darwin who comes to mind, but Albert Einstein, that German physicist with iconic hair. Many of Einstein's theories have stood the test of time, and scientists today make observations that continue to confirm Einstein's theories, including general relativity. This theory says that the force of gravity that holds you and all the objects around you to the ground comes from the effect that matter and energy have on space and time. Now, when Einstein developed this theory in the early 20th century, he assumed that the universe was static in size, an assumption that turned out to be very wrong. It took a while for Einstein to come around to agreeing with many of his colleagues who believed that the universe was, in fact, expanding. Even though Edwin Hubble, an American astronomer, had published strong observational evidence for an expanding universe in 1929, it wasn't until after Einstein visited Hubble and other colleagues at the Mount Wilson Observatory in California in 1931 that Einstein finally admitted his error. According to Einstein's journal, it's likely that he changed his mind after having conversations with fellow theorists, but he also got the chance to take a peek through Hubble's telescope, through which he saw the characteristic signature of an expanding universe, redshifts from the lights of stars in distant galaxies. What are redshifts? Well, they're like the Doppler effect of light. When you're on a busy street corner and a police car directly passes you, the sirens sound high-pitched. But the further away the car gets, the lower pitched the sirens become. This is the result of stretching of sound waves from higher frequencies to lower frequencies, the Doppler effect. Similarly, when a galaxy at the edge of our universe speeds away from our galaxy, its light waves are stretched from higher frequency light waves like blue to lower frequency light waves like red, hence the name redshifts. If the universe was static, Hubble wouldn't have observed these shifts at all. The telescope Einstein visited was a 100-inch or 2.5-meter telescope on Mount Wilson, high above the city of Pasadena. At the time, this was a highly advanced telescope and Southern California was still relatively dark. Hubble's telescope remains on Mount Wilson, but now Pasadena has too much light pollution for optical telescopes, so North American astronomers travel all the way to the Atacama Desert in Chile to look through modern telescopes. The Carnegie Observatories, which operated the Mount Wilson telescope, now have a series of telescopes including two giant 6.5-meter telescopes there. Hubble's observations were truly astonishing, but his work was not the end of the story. Although he was correct that the universe is expanding, his measurements of how fast were incorrect, or to be more precise, his measurement of the value that bears his name, the Hubble constant, was not very precise. The more precisely and the more accurately astronomers can measure this value, the better able they are to calculate the age of the universe and how fast it's expanding. So it's become a major focus in contemporary astronomy to measure the Hubble constant with greater degrees of accuracy and precision. I'll give you just one example. Wendy Friedman was one of the leaders of the key project of the Hubble Space Telescope, the orbiting telescope that NASA launched to enable astronomers to gaze at the heavens from above the Earth's atmosphere. The key to measuring the Hubble constant is to determine the distance of faraway stars and galaxies very precisely, and then to measure the redshifts of those galaxies. Measuring redshifts is straightforward. If the star is standing still, it would have one spectrum, but if it's moving, it has another, which is shifted toward the red wavelength. Scientists compare these two measurements to calculate redshifts. The hard part is figuring out the distance to distant stars and galaxies because we don't have many extragalactic reference points. Friedman and her colleagues relied on a simple principle, that the intensity of light decreases as in an inverse square law. For example, a typical candle gives off about 12 lumens if we're right next to it. But if we move 5 meters away, the light will only be about half a lumen. Lumens are a measure of the light source's brightness. Now, this relationship can be used to calculate distances from a light source if we know how bright the candle was originally. We just need a very sensitive light detector. So we measure how much light reached the detector, and then using our knowledge of the light source and the inverse square law, we can calculate the distance. Most stars change their brightness during their lifetimes, going from bright blue to relatively dim red. But a special class of stars called Cepheid variables have an extremely predictable cycle and can be used like the candles in my example. Friedman led a team of 30 astronomers to do just this. They devoted 1,000 hours of Hubble Space Telescope time to measuring the redshifts in the Cepheids, and they calculated a new value for the Hubble constant. They did this by measuring the luminosity of Cepheid variables and saw that their measurement implies that the universe is 13 billion years old. I've included the Hubble telescope paper as optional reading for the course, and I encourage you to look at it. And one thing that really stands out in this paper is that after the team describes their own measurements, in section 7, they give a list of other measurements of the Hubble constant that were measured independently. They note that the values are all pretty similar, and although they try to combine these estimates to come up with the best possible value, one reason they think they're very much on the right track is because multiple independent lines of research point in almost exactly the same direction. There's a lot in common between our first example of measuring adaptations and the second example of discovering and measuring the expansion of the universe. Both involved careful observation, both involved refinement over scientific generations, and both involved multiple independent lines of evidence being brought together. But there are also some significant differences as well. Sometimes scientists talk about big science, science conducted by very large teams of individuals where no one person understands all of the details. Contemporary astronomy is definitely an example of this. On the Hubble Key Project, 30 astronomers collaborated, but there were hundreds of engineers, computer programmers, instrument specialists, NASA mission controllers, and so many others. The knowledge generated by this research program depends on all of them and doesn't live in any one person's mind. In 2013, the Australian Bureau of Meteorology had to add another color to its forecast maps because meteorologists predicted that sections of the country would experience unprecedented heat, over 50 degrees Celsius, 122 degrees Fahrenheit. It's examples like this that convinced many of us that climate change is no hoax. When Hillary Clinton declared that she believed in science at the Democratic National Convention, she followed up by adding, "I believe climate change is real." To many, the most important scientific question isn't how species adapt or how the universe expands, but how climate change is going to affect us in the future. But how do scientists know that climate change is real in the first place? It starts with their utmost confidence in the existence of the greenhouse effect, a theory proposed by the physicist Joseph Fourier almost 200 years ago. The theory says that gases such as carbon dioxide and methane trap the sun's heat in the Earth's atmosphere, much like a greenhouse. Other gases in the atmosphere, like nitrogen and oxygen, which make up the majority of it, can't trap heat as effectively. Carbon dioxide and methane molecules capture the sun's energy by bending and stretching, and eventually they pass this energy on to other molecules as they bump around in our atmosphere. And this motion is heat at the molecular level. So as more of these gases accumulate, they can capture more of the sun's energy and heat builds up. To be clear, the greenhouse effect is mostly a good thing for us. Without it, the planet would be a frozen ball of ice incapable of supporting life. But too much of a good thing can tip the scales in the wrong direction, and we are producing a lot of carbon dioxide, much more than has been in our atmosphere for 400,000 years. You've probably heard the term global warming repeated in the public countless times. The phenomenon of global warming also occasionally gets referred to as an enhanced greenhouse effect. The idea is that increased amounts of carbon dioxide and other greenhouse gases from human activities has and will lead to a warmer Earth. Now, scientists also are nearly certain that global warming is occurring because they've been collecting detailed data on the Earth's temperatures and atmospheric composition since the 19th century. The data comes from ships and buoys in the ocean, land stations, and more recently from satellites. These diverse sources of data all show the same trend, a warming Earth. Numerous forms of evidence also show that global warming has altered and will continue to alter weather patterns around the globe. This evidence generally consists of simulations, observational records, and theories from physics. Take days of extreme heat. The observational record suggests that there's been an upwards trend. And an upwards trend is also in line with theories from physics and simulations, so that leads scientists to have very high confidence when they say that global warming has led to more days of extreme heat. They're less certain, however, when they try to link forest fires to global warming. The observational record for wildfires is patchy and much shorter. Many factors also go into bringing about a wildfire, such as the density of the forest, the amount of rainfall in the region, land management practices. All of these make wildfires difficult to accurately simulate with models. Nevertheless, scientists are fairly sure that global warming is linked to increased forest fires. Now, it's hard for scientists to be as precise in their predictions of the future as in their analysis of the past. Why? Well, for one thing, scientists don't know exactly how much more carbon dioxide we're going to put in the atmosphere in the coming decades. And that's the kind of information they need to use to make precise and accurate predictions. But even relatively low emission scenarios don't look great for some of us. So take the region around Washington, D.C. Scientists say that this region will see twice as many days over 90 degrees between 2041 and 27 compared to the end of last century. That's a change from about 25 days over 90 degrees to about 65 days over 90 degrees. Scientists paint a similar picture for much of the mid-Atlantic and northeastern regions. It's also hard for scientists to make precise predictions about sea level rise because they don't know exactly how large, influential systems like ice sheets in Antarctica and Greenland are going to react to global warming. If these ice sheets were to melt very quickly, then we'd likely see multiple feet of sea level rise by 2100. But if they melt a bit more slowly, we might see only 1 foot of sea level rise by 2100. Both, of course, are terrible scenarios. Regardless, scientists are nearly certain that sea levels will continue to rise. It's just a matter of how much and by when. It's also worth mentioning that many of scientists' past predictions have turned out to be accurate. For example, since 1990, the United Nations Intergovernmental Panel on Climate Change, the IPCC, has published a report every 5 to 7 years outlining up-to-date information on predicted as well as observed changes in our planet's climate. And their predictions for today's global temperatures have turned out to be right in the ballpark. There is obviously a lot of evidence that the Earth is warming. But how do scientists know that it's our fault and not some natural phenomenon? Maybe the sun's emitting more heat, or volcanoes emit large amounts of carbon dioxide when they erupt. Maybe it's their fault. When scientists do their calculations, they factor in these natural causes, and they found that these natural causes alone can't account for all of the warming that we've seen. How sure are they that it's our fault? The latest IPCC report says that scientists are virtually certain, meaning that they're at least 99% sure that natural causes alone cannot account for the observed global warming since 1951. Scientists will never have 100% certainty about any of their theories, and this is part of what makes science science, but we'll be talking about this more in the later weeks of the course. Climate change is already posing problems for us today, but many worry less about themselves and more about their children. And that brings us to the fourth and final core example of this course, the developing minds of our kids, or more specifically, the development of what psychologists call our theory of mind, our ability to ascribe beliefs, desires, knowledge, and intentions to ourselves and to others. Imagine this scene. You just left work and are on your way to meet a couple of friends for dinner. While walking to the restaurant, you pass by a house with a box of books sitting outside. You peruse the titles and pick up a copy of the spy novel, Tinker Tailor Soldier Spy. Now, when you get to the restaurant, you see an empty building with the lights off, so you pick up your phone and you Google the restaurant and you see that it's not closed permanently, but just moved locations. Then you text your friends asking if they knew the restaurant had moved. One responds by texting back, "Going to be late then, sorry." When you finally get to the restaurant, you're the first one there, so you grab a table. The server brings you a menu, and about half an hour later, your two friends walk in. One of them says to you, "Geez, could you be on time next time, please?" Your friends laugh and you give them a hug, and that's the end. Sounds like a pretty ordinary evening, right? On the surface it is, but it also contains many examples of our extraordinary inferential knowledge of other people's minds. How did you know the books were free? You inferred that the owners of the house left them out for people to take for free because that's a common practice in your neighborhood. How did you know to Google the restaurant's location and not just go home? Because you knew that there was more than one explanation for the empty building. How did you guess that your friends didn't know that the restaurant had moved? Well, because they never mentioned it to you when you were making plans and you had just been at the old location 2 weeks prior. How were you not confused by your friend's response to your text, which didn't directly answer your question? Well, you understood that implicit in their answer was that they didn't know. And how did the server know to bring you a menu when you sat down? Because he knew that that's what people expect when they go out to eat. And why didn't you get mad about your friend's statement about being late? Because you knew she was being sarcastic. What you may not know, however, is that very young children are largely incapable of making such complex inferences about what other people know and don't know. Scientists have studied this phenomenon using something they call the false belief task. There are many variations of this task, but a classic one uses candy. Here's how it works. A child is shown a box of a familiar brand of candy and asked what they think is inside. The child will often say the box contains candy. The researcher then opens the box and shows the child that it actually contains something else, say pencils. Then the child's asked what the box actually contains, and they usually get it right. They say it contains pencils. Now, up to this point in the experiment, both kids and adults would have responded the same way. But the next question researchers ask children shows where we part ways. When the researcher asks young children what they think other people would think is in the box, the children often say pencils. Adults, on the other hand, will say that other people will think that it's candy. Even more interestingly, it appears that there's an age at which children start responding more like adults, around 3.5 years old. From this experiment, researchers have concluded that children who are roughly this age or younger have a hard time separating reality from another person's perception of reality. In other words, they can't comprehend how someone could hold a false belief. They think others know what they know. There are many variations of this experiment. In another variation, researchers move an object from one location to another while a person's out of the room, and they ask children where they think that other person will think the object is. Very young children will say they think the other person will think the object's in its new location, not the old one. Now, there are even further variations of the task that put the validity of the original experiment's conclusions into question. So in what researchers call the false photograph task, children are shown a camera on a tripod with an object like a teddy bear in its view. The experimenter acts as if she's taking a photo, and then the teddy bear is replaced with another stuffed animal, say a duck. When asked what the photo will show, 3-year-olds actually struggled to say that the camera would show a picture of the teddy bear when the duck was in front of the camera. In other words, the experiment had the opposite findings of the candy test. This variation has led some researchers to conclude young children have a more general inability to comprehend false beliefs, not just that they can't attribute false beliefs to others. So what this tells us is that even when scientists agree on experimental results, they sometimes interpret these results differently. For many reasons, studying children's minds is no easy task, and researchers have to pay extra close attention to how they design their experiments with children. Children have cognitive limitations, they're easily distracted, and also ethics boards are extra strict when it comes to experiments with children. We've just looked at 4 examples of scientific research drawn from the physical, biological, earth, and behavioral sciences. These are just 4 examples chosen, to be honest, because they're things I find very interesting. But just reflecting on these examples, we can already begin to see the astonishing range of research projects that fall under the heading of science. The research methods used in studying adaptation, the age of the universe, climate change, and theory of mind are different in many ways. Beyond the differences in technique, their domains, their spatial scales, their temporal scales are astonishingly different. Theory of mind develops in a few years, while the light from Cepheid stars can take millions of years to reach the telescope. These differences have led some philosophers to argue that when you take a really close look at scientific practice, you don't find much unity at all. Each discipline or subdiscipline has its own way of looking at the world, and so brings its own tools, methods, and theoretical frameworks to the task. There is certainly some truth to the idea that science is not completely unified and that there is no master method or recipe that's appropriate in all contexts. Nevertheless, there are certain elements common to all of these examples, and exploring these commonalities will be our task in the next weeks. So what are the commonalities? There are at least 4 major ones. First, all 4 of our examples involve sophisticated forms of observation. Adaptation was studied in Galapagos, the universe by observing with telescopes, climate change by considering weather station measurements, and theory of mind by observing children in the laboratory. Second, simple observation wasn't enough. Evolutionary biologists built up samples for further analysis in the lab and then conduct evolution experiments. Astronomers can experiment, but they can use spectroscopy to learn more about the dynamics of their systems. Climate scientists can't perform global experiments, but they can create sophisticated simulations of the planet's climate. And psychologists rely heavily on experiments, but they can't perform just any experiment. They must keep both children and ethics boards in mind. Third, in each case, it was multiple lines of evidence generated using different experimental and observational techniques that convinced the scientific community of the relevant results. Simplistic pictures of science, such as those that are taught in high school, make it seem like scientific research miraculously uncovers the truth by simply verifying one hypothesis with a single experiment. While this does happen occasionally, research more often looks like the cases I've talked about. Research done by multiple people using different approaches that point in the same direction, or they don't sometimes, like in the case of children's beliefs. Philosophers call this robustness or consilience. Fourth and finally, all of our examples involve the accumulation of evidence over time. Each case involves scientific understanding that improves over time, from an initial sense that the answer is at hand, to greater accuracy and precision in measurements, and a much greater appreciation of what is genuinely needed to explain a phenomenon. While scientists never achieve certainty, this is reserved for logic and mathematics, the accumulation of evidence, especially from multiple independent sources, is the key to increasing confidence that a hypothesis is true. Next week, we will delve much deeper into these issues. We are going to look at the 3 main sources of scientific knowledge: observations, experiments, and simulations, and we will talk about how all of them are examples of empirical knowledge. Let's start this week off by imagining a scenario. You're about to travel overseas to live in a country where hepatitis B infections are common. Your doctor recommends that you get the hepatitis B vaccine, so you get the vaccine prior to starting your new life abroad. But less than a year later, you start to feel tired regardless of how much you've slept. You also start to experience blurred vision and tingling in your limbs. Over a few more months, your symptoms only get worse. So you go to the doctor, and after a number of tests, you're diagnosed with multiple sclerosis, a chronic and potentially fatal disease, and a disease with a cause currently unknown to scientists and doctors. While researching your condition, you come across articles about a Frenchman who, much like you, was diagnosed with MS less than 2 years after receiving this vaccine. You also read that the man's family is now suing the manufacturer of the vaccine for causing his untimely death. So you decide to sue the manufacturer too. What kind of evidence would you need to show that the hepatitis vaccine caused you to develop MS? At this point, all you have is circumstantial evidence. You and at least one other person were diagnosed with MS after receiving the hepatitis B vaccine. What you don't have is causal evidence, which could rule out that you developed MS after getting the hepatitis B vaccine coincidentally. To be clear, the World Health Organization and the United States Centers for Disease Control and Prevention argue that scientific evidence says that hepatitis B vaccine does not cause MS. But let's just say you wanted to take a look at the evidence yourself. Where would you start? The U.S. National Research Council's Manual on Scientific Evidence advises lawyers and judges about how scientists produce evidence that shows one event likely caused or likely didn't cause another. The manual says that the gold standard for determining the relationship between a drug or vaccine and a negative or positive health outcome is what scientists call a randomized or clinical trial. A randomized trial, clinical trial, or true experiment is considered the gold standard for determining the relationship of an agent to a health outcome or adverse side effect. So to make the case that the hepatitis B vaccine caused you to develop MS, you would need to closely examine the randomized trials the drug manufacturer conducted when developing its vaccine. You would do so by scouring peer-reviewed journals for studies summarizing the methods and the results of these trials. Now let's take a step back here. What's a randomized trial? Why does the National Research Council think it's the gold standard of evidence? And what's peer review? We'll talk about these topics in greater detail later, but here's the answer in a nutshell. Randomized trial entails trying out a drug or medical treatment on half of the experimental subjects, and which half any given person is assigned to is chosen randomly. The best randomized trials are also double-blind. This means that neither the experimenters nor the participants know who's getting the real treatment and who's getting the placebo. Only a third party or a computer knows this information. And these trials should be published in a peer-reviewed scientific journal. This means that other scientists who don't know or have conflicts of interest with the experimenters evaluate whether the study is soundly conducted and thus whether it's worthy of publication. But why is this very refined set of quality control standards so highly regarded? And why do we think this kind of scientific investigation is a good guide for something as important as medical intervention? Randomized trials are an expression of the scientific community's broader commitment to what I will call scientific empiricism. This is the idea that all of our scientific knowledge should ultimately come from unbiased observations of the world. Now, the key word here is unbiased. By randomizing who gets the drug in question, who knows who's getting the drug in question, and who reviews the merit of the trial after it's over, these kinds of experiments aim to remove bias inherent in this or any human activity. Now, some argue science isn't the only means to knowledge. Some say that knowledge can come from mathematics, which is based in pure thought. Others argue that knowledge can come from poetry, art, or divine intervention. But this class isn't about the philosophy of mathematics or religion or aesthetics, so we're not going to discuss pure thinking, divine inspiration, or poetry. This week, instead, we're going to focus on how scientists produce knowledge through observations, experiments, and simulations. When I use the term scientific empiricism, I'm describing a fundamental scientific principle, the principle that scientific knowledge has to be grounded in observation. This view of the sciences has ancient roots, but in its modern form, it's associated with the scientific revolution, which took place in the 16th and 17th centuries. Our earliest scientific traditions put greater emphasis on pure thought and pure mathematics as being on par with or even superior to observation. But during the scientific revolution, natural philosophers, what we now call scientists, gradually came to prioritize observation and experiment as the best means to grounding scientific knowledge. Now, you might have noticed that I've mentioned the terms grounding or grounded a few times. What does this mean? To say that science is grounded in experience is a metaphor, but it's a useful one. The metaphor refers to the foundation of scientific knowledge, what this course is all about. Just as a concrete slab might be the foundation for a house, scientific empiricism says that scientific knowledge is built on a foundation of observation. Ultimately, no matter how abstract, general, complex, or mathematical they are, scientific laws, theories, and models have to ultimately be tied back to observations of our world. And if a building's foundation is faulty, it will collapse. So too with science. Grounding scientific knowledge in observation is supposed to ensure that science is built on a stable foundation. So why is observation thought to be this bedrock of science? The first reason is that observations are public, as opposed to the products of pure thought. In principle, other people should be able to see the same things you see and repeat an observation or an experiment to get the same results. And the second reason is that public observation ought to be free of bias. Although any one person might see what they want to see, public or shared observations should cancel out a lot of this bias. Scientists can also create controls and checks to eliminate potential sources of bias, which is exactly what randomized trials, for example, aim to do. The third reason is that we do science to learn about the world itself, not about the products of our own minds. In other words, we need to observe to get knowledge about the target domain of science itself, which is the natural, observable world. Now, in the next part, we're going to dive deeper into the many ways that scientists observe. Scientific empiricism tells us that the foundation of scientific knowledge is observational. So let's dig a little deeper into this claim and look at three sources of scientific knowledge: simple or straight observation, experimentation, and simulation. Let's start with observation. Straight observation, or what I will simply call observation most of the time, is the most fundamental source of scientific knowledge. It involves using our senses, perhaps augmented with instrumentation, to discover what happened in the past, what is happening now, and to discover patterns and dependencies. To be a little more precise, scientists observe single instances or snapshots of the way that the world is. And very generally, we can call these things events. But scientists often make repeated observations or look for patterns and distributions in their observations. These more generalized observations are called phenomena. I've already talked about Charles Darwin's remarkable work in the Galapagos Archipelago, but we haven't yet looked at Darwin's own words. Here are the opening words of Darwin's famous book On the Origin of Species. When on board HMS Beagle as naturalist, I was much struck with certain facts in the distribution of the inhabitants of South America and in the geological relations of the present to the past inhabitants of that continent. These facts seem to me to throw some light on the origin of species, that mystery of mysteries, as it has been called by one of our greatest philosophers. On my return home, it occurred to me in 1837 that something might perhaps be made out on this question by patiently accumulating and reflecting on all sorts of facts which could possibly have any bearing on it. Now notice what Darwin tells us here. The basis of his revolutionary theory was pure observation. He was struck with certain facts in the distribution of the plants and animals in South America. I've already talked about Darwin's observation in some detail, but let me remind you about one of his most important observations. Darwin noticed that giant tortoises on different islands had different shell shapes, and that mockingbirds on different islands had different beak shapes. His observations of tortoises, mockingbirds, and later finches formed the basis of his ideas about evolution. Darwin realized that the distribution of different species on different islands reflected common ancestors and subsequent evolutionary processes. And he was able to do this by careful observation, unaided by fancy equipment, only his naked eyes. He did enhance his observations with collections, and these could be analyzed later, and with careful notes from which he could look for patterns. But he didn't really use any instruments in Galapagos, and in his later work, he simply added a standard microscope to the mix. Not all observations look like this. Modern astronomers rely on incredibly sophisticated instruments, telescopes, in order to make observations. Let's take a look at some of the largest and most sophisticated telescopes ever built at the Las Campanas Observatory in Chile.
As you well know, most people think of a telescope as being something that the pirates have, that they open it up and they're looking through a lens and they're looking out and holding it. That has its practical limits. A piece of glass as a magnifying lens is heavy, and you have to polish both sides of it. There's another way of focusing light, and that's through a mirror. And in that case, you only have to polish one side, so it's easier, but you can also support it, and you can make it bigger and bigger and bigger and have a lot of structure behind it. So here we have one. It's inside of this enclosure, and the reason that you just don't put it outside is that you have to protect it, first of all, from the heat of the sun during the day. You have to protect it against dust that's blowing around. But at night, you want to open it up. And so these telescopes have enormous areas of the telescope structure that are open to the atmosphere. And this one in particular has louvers in it, which can open up and make the telescope dome almost transparent to wind, that once you open it up, the wind can just flow through and right through the dome. So there's been a lot of interesting technological developments as you come to understand what causes the shimmering of the light and the distortion of the images. And we can now build telescopes that are sort of synergistic with their environment, because they impact the mountain, they block the wind, they change the heating patterns. And knowing that, you can build these telescopes in a non-intuitive way, but in a way that the computers understand what's going on, they can correct for things. And having them on the ground is an advantage over having them in space, because as technology changes, as new detectors are developed, you can bring them to the telescope. One's in space, they're usually inaccessible after a certain period of time. And the only way to put something better into space is to put something new into space. Whereas here you have a large telescope, which is a workhorse, but you can put different and new things on it all the time.
Why do astronomers go through the trouble of using such complex and expensive tools? Well, the bigger the telescope, the bigger the mirror. The bigger the mirror, the fainter the light that can be detected. And the fainter the light, the further away and further back in time we can observe. This is an example of what philosopher Paul Humphreys calls extending ourselves. Humphreys writes, "One of science's most important epistemological and metaphysical achievements has been its success in enlarging the range of our natural human abilities. And while this is true across many different sciences, it's especially true for astronomy. Few fields have harnessed the power of technology and computational power to extend our senses across scale and time and sensory domains as extensively as astrophysics." Why does astronomy or astrophysics require so much augmentation? Well, astronomical objects are simultaneously visible, but also hard to detect. Objects such as galaxies are enormous. They're often 100,000 or 1,000,000 light years in diameter. And astronomical objects of interest are very, very far away. For example, this galaxy, 2 Zwicky 28, is more than 391 million light years away. This distance also means that the events we would need to observe happened a very long time ago. So astronomical observation involves trying to get a grip on objects that are very large, very far away, and whose present state has to be inferred from events in the far, far past. Even more profound challenges stem from the fact that astronomers cannot manipulate stars and galaxies. They only can observe what's already happened. So all scientific methods, which are observation-based, face this kind of challenge. The challenge is that their experimental subjects can't be manipulated. Scientists can only see the configurations that nature's already provided. No new ones can be created. So astronomy inherits this problem, but it's even more complicated in astronomy because in nearly every case, there's only a single vantage point, on or near the Earth. And from this vantage point, you have to look at what's happened at a fixed time in the past. We've talked about extending our observations using technology. But there's also a more old-fashioned way to extend ourselves: practice. Scientists who work in sciences that heavily rely on observations, paleontologists, geologists, ecologists, and even those that need complex apparatuses, astronomers, spectroscopers, particle physicists, they often report radical and sudden changes in their observational abilities with practice. In his wonderful book, Your Inner Fish, the paleontologist Neil Shubin talks about how difficult it is for young paleontologists, or even experienced ones who are working in new places, to notice the salient features. He describes his experiences of working in the Arctic tundra for the first time. For a long, long time, it all looks the same. And then all of a sudden, one day, he sees geological strata and the differences between fossils and bare rocks. And this is really similar to the experience that musicians and athletes often report. They'll try and try and try to achieve something which just seems impossible, day after day. And then all of a sudden, one day, it's not only possible, but it seems totally straightforward. So just as a telescope can enhance our ability to see, so can practice. And this is mostly good for science, but I do want to flag a philosophical issue for us to discuss. Remember that one of the justifications for scientific empiricism is that observations are public. We build our scientific knowledge out of something that we can all share. At least in principle, other people can always see the same things that we can see, and anyone can always repeat these same observations or experiments that brought us to the beliefs that we have. But if experts literally can see things that the rest of us can't see, then this creates some tension in this view. It's still true that anyone in principle can repeat the observation, but this might require the same training as the initial observer. Is simple observation, even with fancy equipment, an efficient way to find out about the world? You might think not. If what you're trying to observe is rare, then waiting for it to happen might mean waiting a very, very long time. This is, of course, one of the primary reasons that scientists engage in experiments. But it's not always possible to do experiments. If you want to study something that's happened in the past, or something that takes place far away, then there's really no point in even talking about experiments. So is there a way to make simple observations more efficient? The general answer is yes. As scientific disciplines progress, they can become more efficient or more systematic at observing the subject matter. Well, how does that happen? This varies by discipline, but there are at least 3 common ways. First, as scientific disciplines mature, they build up general knowledge in the forms of models and theories, and this gives scientists clues about where to look. Darwin had to practically stumble into the evidence for evolution, but now we know that island chains are a good place to look for it. A second way that observation can be enhanced is through coordination between large groups of scientists. We often don't think about it, but telegraphs, telephones, and especially the internet fundamentally changed the way that science is conducted. As soon as astronomers at Les Campanas detected the possibility of a neutron star collision, they let their colleagues all over the world know about it. And this resulted in a collaboration of 3,674 researchers from over 900 institutions. Sometimes just having extra eyes, or in this case, hundreds of extra eyes, improves our ability to observe. Finally, in some cases, observation can be automated, semi-automated, or crowdsourced. Automated image tagging is familiar to us from Google image search and related internet technologies. As anyone who's done an image search knows, these can be more or less successful depending on the complexity of the image. A good example of crowdsourcing is a project called Galaxy Zoo. The Sloan Digital Sky Survey systematically imaged large portions of the northern and southern skies using relatively large telescopes. Millions of images were generated, far too many for even a large team to examine. So interested members of the general public can tag images of galaxies that have been collected with this project, and then researchers can look at the ones that have been tagged in the most promising ways. So far, I've talked a lot about observations and how we can improve them, but we often observe in order to learn something about causal relationships. What depends on what? I'm going to finish our discussion of observations by introducing a framework that we can use to understand how scientists make inferences based on their observations, experiments, and simulations. The logic of observation-based inferences was described by John Stuart Mill, a philosopher best known for writing about liberty, but who also made great contributions to how we think about science. Mill was interested in how we can use observations and experiments to determine causes, or what depends on what. He introduced a series of methods for reasoning about empirical data, which we now call Mill's methods. I'll talk about the first 2 of his methods, what we now call the method of agreement and the method of disagreement. So to begin thinking about these methods, let's distinguish between outcomes and conditions. Let's imagine there was an outbreak of food poisoning in a local restaurant. The fact that people got ill is the outcome. The different foods that people ate, the different restaurants they ate in, and the health histories of the people are the conditions. Scientists often call the outcomes dependent variables and the varying conditions independent variables, and I'll use these terms. So Mill's method of agreement is simple. Make a table of the dependent and independent variables, and then see what independent variables are shared by all the cases with the same dependent variable. If there is such a variable, Mill's method of agreement identifies this as the cause. So let's look at a simple example with just 4 dependent variables and 1 independent variable, whether or not an individual got sick. In this case, Mill's method of agreement would flag tofu as the likely cause of illness. It's the one food all the people who got sick ate. Now let's look at Mill's method of disagreement. It's closely related. We make the same table of dependent and independent variables, but in this case, we look for a pattern where a difference in the dependent variable only occurs when there's a difference in a single variable. In this case, Mill's method of disagreement would flag noodles as the likely cause of illness, because Wei was the only person who got sick and the only person who ate noodles. Although Mill's methods begin to give us a logic for thinking about observation systematically, they're still based on a very simple idea. When we're interested in what causes a phenomenon to occur, we look for other factors that occurred or didn't occur with it. And this gives us prima facie evidence about the cause, meaning it's a starting point for understanding what depends on what. Mill's methods definitely don't settle the matter. These patterns of observations are consistent with other scenarios, including one where we haven't yet thought of the relevant factor, so there's a hidden cause, or there's some upstream common cause. We'll return to these points later, but first let's talk in more detail about experiments. Toward the end of my discussion of observations, I asked whether simple observations, even with fancy equipment, is an efficient way to find out about the world. If what you're trying to observe is rare, then waiting for it to happen might mean waiting for a very long time. I talked about some of the ways that scientists can make their observations more efficient, but there are always going to be intrinsic limitations when one's methods are confined to simple observations. Think about it in terms of Mill's methods. If there's a combination of variables that we want to consider, but we haven't observed them and we don't know where to observe them, we're going to have to wait a long time, maybe even a lifetime, in order to get these observations. But what if we could produce the combinations of variables that we were most interested in? Experiments are what allow scientists to do this. They allow scientists to generate the conditions that they want to observe by intervening on phenomena. There are at least two reasons why experimental interventions are so important. The first is that scientists use experiments to create new phenomena. And the second is to use experiments to isolate existing phenomena from the rest of the world. So in the first case, scientists sometimes literally create a phenomenon. They can bring into existence a constellation of things that they wish to study. So this can be done, let's say, by generating a mutation or making a new molecule. In some cases, the novel phenomenon does exist somewhere in nature, but it's so rare it's hard to find. But there are cases, such as when scientists synthesize completely new molecules, that something genuinely new to the universe is created. The second kind of case is when we use experiments to isolate. This allows observations of nature to take place in a highly controlled manner, isolating the phenomenon of interest from many other factors, especially ones it commonly co-occurs with. Now, this is a very abstract characterization of experiments. To get clearer on it, let's visit a modern evolutionary genetics laboratory here at the University of Pennsylvania.
How do we make these flies that encode the wrong species version of only a single gene? What we do is inject into an embryo 3 different components. One is called Cas9, a protein that's effectively molecular scissors that we're going to use to cut out the native version of this gene. Second, we have RNAs that are cognate, or they match the sequence of the gene that we're trying to target. And these RNAs guide the Cas9 molecular scissors to the site we're trying to manipulate. Finally, we have a third component, which is DNA derived from the wrong species that is used effectively as a template for the repair process. So the molecular scissors go in and cut out the gene of interest, and this third component provides a template from the wrong species that's then copied in to that genome. In the end, we're left with a fly that has the contemporary genes and telomeres of Drosophila melanogaster, but only at this one gene, the wrong species version. And in this carefully engineered fly, we're able to very precisely hone in on the biology that has changed as a consequence of the evolution since these 2 species split.
We learned from Professor Levine a little more about what a cutting-edge genetics laboratory looks like. In her laboratory, she studies the evolution of the proteins attached to the end of chromosomes. And in doing so, she illustrates the 2 reasons for turning to experiments that I mentioned earlier. The first is isolation. She isolates a specific phenomenon in a model species. She's looking at the behavior of proteins on the end of laboratory fruit flies' chromosomes. And she also creates a phenomena. She creates new genetic variations to study by using the technique of CRISPR-Cas9, which lets her alter the DNA sequence of the fruit flies. This is, of course, just one laboratory, but we'd see the same kinds of motivations for experimentation in labs throughout the world. I hope that our detailed look at the evolutionary genetics in the Levine lab, as well as our discussion of theory earlier, has given us some background to develop good intuitions about the nature of experiments. But since we're doing philosophy of science, I want to get abstract a bit and think about how we should characterize experiments more generally. I've already explained the core of an experiment is an intervention. In order to think about the logic of experiments, we're going to need to make an idealization. We have to deliberately simplify something in order to understand it better. The idealization we are going to use comes from philosopher Jim Woodward, what he calls an ideal intervention. An ideal intervention is, speaking metaphorically, a surgical intervention. We have complete control of experimental variables, and when we intend to change one of them, we only change that one, and anything else that causally depends on it. With the idea of an ideal intervention in mind, we can begin to think about the logic of experiments by returning once again to Mill's methods. In fact, we can return to the unfortunate example of everyone getting sick from the tofu. In general, tofu doesn't make people sick. In fact, it's an essential part of many people's diets. So something obviously went wrong in this case. And one thing we might try to do is go back to the particular situation and derive some clues. But another thing we might do is to create an experiment and to find out under what kinds of conditions illness-causing bacteria like E. coli or Listeria can grow on tofu. So let's imagine an experiment. In this experiment, we might test tofu under 5 different conditions. Just taken out of the refrigerator, left on the counter for 30 minutes, left on the counter for 2 hours, left on the counter for 10 hours, and cooked to 75 degrees C. In principle, we could wait around to find tofu in each of these conditions, but a much more efficient way is to create the conditions we want to investigate. So we would take our tofu, probably many pieces, and subject them to the 5 different conditions, and then do a test for bacteria under each condition. So we can infer from this experiment that bacteria can grow at room temperature, and while these bacteria aren't an immediate danger to humans, we need to be very careful about leaving tofu at room temperature for very long. If this were a real experiment, and not just a simple example, we'd probably go into a lot more depth trying to determine how long it takes for bacteria to start growing, when the dangerous ones are present, and what can be done to minimize health risks. But what I hope to have shown you is that the logic of experiments is just like the logic of observations, the application of Mill's methods. Now let's recall what happened in the Levine lab.
What my lab does instead is we take versions of that gene from closely related species, put it back into Drosophila melanogaster, and ask what breaks. And we think that what breaks when we put the wrong species version of that gene into our model organism, that tells us what's the biology that evolution has shaped in the past 500,000 to 2 million years of evolution. And we're using this approach to study specifically the proteins that package chromosome ends, or telomeres. So we are specifically interested in genes that encode proteins that glom onto the DNA.
So we can see that from the simple example of tofu to the complex example in a modern genetics laboratory, much of the logic of experiments is the same. You might be wondering why I haven't mentioned statistics as I've discussed the logic of experiments. A lot of modern experiments, of course, do involve statistics. And why do they? Well, some effects don't show up every time, or are hard to detect, or there are causal factors that are hard to control. And in all of these cases, scientists need to use statistical methods to tease out the signal from the noise. This is a huge topic worthy of its own discussion, its own course even, and we're not going to be able to discuss it other than to say that the basic logic remains the same, even if we need to introduce the mathematics of statistics. Before moving on, we need to talk a little bit more about causation. I've spoken very loosely about how observational and experimental methods help scientists find out what caused something to happen, food poisoning in our example, or chromosome integrity in Professor Levine's lab. Mill's methods are a helpful guide to finding causes, but they do break down as a guide in certain circumstances. And one of the most well-studied cases is situations where you have a common cause. So here's an example. A lot of the time when it rains or is about to rain, I get a migraine. For some people, the connection between migraines and storms is like clockwork, and I'm sorry if you're one of these people. It's totally awful. So let's say over the course of a month, we made a Mill-style chart of migraines and storms. And we would see on this chart a link. Migraines and storms are highly correlated. But if we weren't careful, we could end up inferring that migraines cause storms, just the way we inferred that illness-causing bacteria grow at room temperature. In other words, correlations only tell us two things co-occur. They don't tell us what depends on what, or even if there is a causal relationship at all between the two variables. Now, everybody knows that migraines don't cause storms, and storms don't cause migraines, and yet they're highly correlated. Well, what explains this? The explanation is that they have a common cause. Sudden drops in atmospheric pressure cause both migraines and storms. In this kind of case, where there's a common cause that hasn't been explicitly considered, Mill's methods will not uncover causes, only correlations. And it's because of this that you may have learned that correlation doesn't equal causation. That statement is true, although as we've seen, correlation is a good guide to causation. So before moving on, I want to raise one more issue about experiments. When most of us were in high school, we learned about what teachers called the scientific method. It was taught in a pretty formulaic way. Do some background research, formulate a hypothesis, test the hypothesis with an experiment, and then conclude that the hypothesis was true or false. I hope our time together so far has convinced you that this is a massively overly simplified picture of what scientific research looks like. But I do want to briefly focus on one particular oversimplification in this formula. When we're taught the method, we are taught that the purpose of doing experiments is to always test hypotheses. But is this true? I think the answer is simple, no. Lots of experiments do test hypotheses, but lots of other experiments, as well as straight observations and simulations, are exploratory or align with theories in more complex ways. Scientific results are often written up talking about the connection between theories or hypotheses on the one hand and experiments on the other, but that doesn't mean that this is literally the method or procedure that has to be used in every case. In the next part, we're going to talk about simulations, something you may not have learned about at all in high school. The third source of scientific knowledge is simulation. While there are many historically important analog simulations run on mechanical models, I'm going to focus on computer simulations. At its core, a simulation consists of a model and initial conditions. We can think of a model as a representation of some real or imagined part of the world, and the initial conditions as the starting point. Let's take a simple and famous example to begin with. The economist Thomas Schelling presented a very simple model that shows how racial segregation can occur in cities even when little racism is present. To be clear, he didn't argue that cities don't have racism, only that extensive racial segregation can happen even when cities are very, but not completely, racially tolerant. His model was agent-based, meaning that individuals are explicitly represented in the model. The model represents a city as a grid and people as colored dots on the grid. So let's use blue and green people. We also need to define neighborhoods. Each individual has its neighborhood consisting of the 8 adjacent squares, what's called the Moore neighborhood in this literature. Every individual prefers that at least 30% of its neighbors be of the same type. The blue ones want to have 30% or more blue neighbors, and the green ones want to have 30% or more green neighbors. No one particularly cares about being in a homogeneous neighborhood or even having the majority of neighbors look alike. Now we need to know 2 more things to understand the simulation. First, how do the agents move in this model? Remember, their preference is for having 30% or more like neighbors. In each time step of the model, every agent considers its neighbors and decides whether or not this threshold has been met. If it has, the agent does nothing, and if it hasn't, then the agent moves to the nearest open space. The second thing we need are the initial conditions, how the agents are initially distributed on the grid. The simplest way to work with this model is to randomize the initial placement of agents, and then repeatedly run the simulation with a different random configuration. Let's watch what happens. As we saw in these examples, Schelling's model shows that the non-segregated state is very unstable. Even when most agents are initially satisfied with their neighbors, they can become disgruntled as soon as a neighbor leaves or a new one moves in. And this leads to the new agents becoming disgruntled. So a small patch of dissatisfaction results in widespread dissatisfaction and widespread movement, and ultimately segregation. Though there are a few grid configurations that are integrated where every agent is happy, these are extremely rare and impossible to find randomly. Thus, Schelling's major result is that small preferences for similarity can lead to massive segregation. And this result is quite robust, meaning it occurs across many changes to the model, including different tolerance thresholds, different rules for movement, differing neighborhood sizes, different spatial considerations, and so forth. In fact, it's extremely hard to avoid segregation when agents have some preference at all for neighbors like themselves. Now, Schelling's simulation is very simple, but it illustrates very well how simulations are put together and what we can learn from them. All of the same principles apply to something more complex. For example, I talked in the past about the phenomenon of global warming. And when scientists want to make predictions about changes to future climates, they of course can't do experiments that directly bear on the subject. So instead, they use simulations, much more complicated than Schelling's, but still fundamentally the same. Specifically, they start with a model of the climate. This has to take into account all of the air in the atmosphere, the oceans, the incoming solar radiation, the land masses, many other things that influence the weather and the climate. And then this model has to represent how energy is transferred through the system and how this in turn changes climatic variables including temperature, rainfall, and sea levels. If you'd followed the discussions of climate change, you might know that there's no single simulation or model in use. So why is that? The reason is the enormous complexity of the climate. The climate's what scientists call a complex system, which means it's composed of a very large number of interacting parts. This means that there's no way to fully and realistically simulate the system, so approximations have to be made. And while there's no disagreement about the physical structure of the Earth or the physics of energy transfer, there are different ways to make approximations. So the result is that multiple, but closely related, distinct models differ in how the complexity is simplified. And I want to come back to this point. So as we saw in the Schelling case, we also need to include initial conditions and other inputs to the model. Climate models are often initialized with past climate records, but to make predictions about the future, climate scientists need to know how much carbon will continue to burn. Since that's of course unknown, they actually run the model with different scenarios. For example, increased emissions over the next 50 years, steady emissions over the next 50 years, reduction by 25%, and so forth. Like the Schelling simulation, climate simulations are run multiple times, randomizing some variables and looking for general trends in the outputs. Moreover, since there's no one master model behind all the simulations, each of the major models has to be tried out. This is the basis for graphs like this one that show massive increases in the global mean temperature unless there are drastic reductions in carbon emissions in the near future. Notice that there are multiple lines in this graph. This corresponds to results from models that considered how much carbon we end up emitting among other variables. Having now talked about two simulations, a simple one and a highly complex one, let's pull back and ask some philosophical questions about them. Specifically, are they really empirical, and how can we be sure if they're reliable? First, let's talk about the extent to which simulations are empirical. I've argued that science gets a lot of its power from its empiricism, its ultimate foundation in public observations of the world. But simulations look different. They start from a model, which is often represented in a computer, and they don't carry out any conventional observation. Instead, scientists use simulations to compute what happens in a model given some initial conditions. Ultimately, it looks like we're doing math here, not observation. Something's clearly right about this, but there's certainly a difference in procedure. Simulations don't require us to go out in the field to observe, or even to manipulate them in a laboratory. But there are some important similarities between experiments and simulations. In both cases, scientists create conditions to test what happens when one or just a few variables are manipulated. Moreover, although experimental systems are physically in the world in the way that most models are not, experimental manipulations happen on experimental systems which are often modified versions of what we'd find in the wild. For example, the Levine Lab fruit flies are real fruit flies, but they've been bred for laboratory purposes. We would never find these particular flies in nature unless one escaped. So this means that in both experiments and simulations, we need to make an additional inferential step about the world from what we've learned by manipulating a system, be it an experimental system like a laboratory fruit fly or the model at the heart of a simulation. There's another way that many simulations are grounded in public observations. The components of models and the initial conditions of the models are of course based on prior observations about the world. In some cases, like in climate simulations, the long accumulated knowledge of many different scientific fields is used to create the model, and observations are used to give the simulation its initial conditions. And in other kinds of models, like shelling simulation, very simple descriptions of how people might behave are used to construct the model. So if we would want to draw inferences on the basis of this simulation, we'd have to investigate whether the social and psychological assumptions in the model have any real relationship to real communities. So in the end, despite possibly seeming non-empirical, simulations really are thoroughly empirical. We can think of simulations as a tool for exploring the consequences of facts that we have determined empirically or facts that we would need to further investigate empirically. One final question about simulations. Are they reliable? Can we count on them as a guide to making decisions about the future or using them to intervene in matters of health or public policy? There are two versions of this question. The first concerns particular simulations. It's always a good idea to ask about the quality of a simulation. As a non-expert, usually the best we could do is evaluate the reliability of the research team who performed the simulation, or maybe the venue in which it's published. Do they have a track record? Do they have an ulterior motive or agenda? But the philosophical question is a deeper one. Simulations often take what is known about the past behavior of systems and use them to make predictions about new scenarios, including new domains, new people, or the future. This is definitely a real question, but it's part of a nexus of quite general questions about scientific inference. These questions include, how do we know we haven't neglected some important process or factor that will be important in the future? How do we know that the future will resemble the past in the important respects? And when we move from one system, say fruit flies in the lab, to another, say fruit flies in nature, how do we know that there isn't an additional consideration we've neglected? These are deep and important questions, the answers to which are never definitive. The epistemic power of science does not come in having definite ways to deal with all of these issues once and for all. Rather, it comes from a general posture of openness. Openness to the possibility that some as yet undiscovered factor will prove to be important, that the future may differ in some important respect from the past, and so forth. And this is why scientists say that their results should always be taken to be provisional, even when they're well supported. And this is a theme that we'll continue to return to when we discuss objectivity. I want to return to a philosophical worry about scientific empiricism. Remember that scientific empiricism is the claim that all scientific knowledge is grounded in observations. Now, why is that? Because observations in the form of straight observations, experiments, and simulations provide the foundation on which scientific knowledge is constructed. This is a very powerful picture and has guided our discussion so far, but I want to think some more about this. This picture presupposes that we can neatly separate observations from the rest of science. Specifically, that we can separate observations from hypotheses, theories, techniques, background knowledge, and so forth. And is this really true? An important challenge to this idea was raised by Grover Maxwell, a 20th century philosopher of science. He argued that if observations were truly the foundations of science, then there ought to be a sharp distinction between what's observable and what's not. The scientific entities that are not observable, like electrons, quarks, and genes, can't provide the foundations for our knowledge if it's supposed to be based on observations. So is there some place we can draw the line between what's observable and what's not? Maxwell argued no. He said that while the notion of what's observable is intuitive, it's impossible to draw a plausible line between what's observable and what isn't. So take a paradigm case of what's observable, the tree outside my window. In order for me to see the tree, photons have to bounce off the tree and hit my retina. And this is an entirely inert process. Some light gets absorbed by the molecules in the atmosphere and in the glass of the window, and that already tells us something interesting, but let's set this aside for now. As you can see, I wear glasses, so for me, an image of the tree is going to be refracted, which means that it's distorted physically by my glasses in order to correct for the shape of my eyes, which themselves distort the image. So this means that the image hitting my retina has been substantially changed, but changed in a way that preserves the image of the tree. This all seems like observation still, but it already shows that it's not completely straightforward. Now, what if I was looking at a distant tree and had to use binoculars or a telescope? They add more magnification and allow focusing on specific objects in the distance, and they also extend and correct our typical optical powers using the technology of lenses. But they don't change light into another form, so perhaps this is still observation. Now let's think about telescopes. In some ways, they're no different than binoculars or land-based optical telescopes. They still collect and focus light, but the major difference is that instead of looking through them, we attach a digital camera to them. The digital camera plays the role of our eyes. It collects the photons and creates an image. And then this image appears on a screen, and then we look at the image on the screen. So there's small technological changes again. Are we still observing? Well, it seems so, but there's definitely distance. Now let's make another change to the very small instead of the very far away. Looking through a magnifying glass or an optical microscope. Did anything fundamentally change when we looked through a microscope? Well, it doesn't seem so. How about an electron microscope? Well, now something very interesting's happened. We're no longer using photons or light to see, but electrons, which we typically wouldn't consider observable. And yet, we can use electron microscopes and optical microscopes to look at the same object, and they look the same. And we can continue this kind of overlap argument deeper and deeper into the domain that we would not normally describe as observable. So what's the upshot of this? Well, in my view, it means that we shouldn't understand observation as the same thing as seeing. And we especially shouldn't understand it as seeing with the naked eye. Observation instead should be thought of as reliable detection. We observe in this technical sense when we use a combination of our senses and technology to reliably detect something in the world. Understood this way, in some domains, sensors or video cameras are often more reliable than our own senses. So when we say that the foundation of science is empirical or observational, we should understand it in this way. The foundation is the reliable detection of what's in the world. Throughout our discussion, I've mentioned how observation, experiment, and simulation relates to questions regarding objectivity. And this is no surprise. Some philosophers of science argue that ultimately all questions in their field relate back to the question of whether or not science is objective. In our coming discussions, we'll consider these topics in more detail. In the last part of this course, we talked about how science is conducted, but we didn't cover why it's conducted. And I bet the answer to this question seems obvious. To learn about the world, of course. What else could it be? As a philosopher, part of my job is to analyze some of our deepest held assumptions. So let's pause for a moment to think about what it means to say that science aims to learn about the world. The key word here is aims. Scientists certainly aim to uncover truths about the world, but are we sure that science does in fact tell us what the world is really like? Scientists have been wrong in the past, so how do we know that they're not wrong now? In one sense, this is what philosophers mean when they say that science is objective. Scientific knowledge is objective if it tells us what the world is really like. And this is opposed to some particular scientist's subjective take on the world, some particular point of view. But this isn't the only thing philosophers mean when they say that science is objective. We also debate the objectivity of the scientific process itself. When we talk about objectivity in this sense, we're asking questions about whether scientists and their methods are unbiased. In the last part of the course, we talked about the second sense of the term objectivity, objectivity as it relates to the scientific process. For example, we talked about how observation is the foundation of science because observation is public. Public observation should, at least in theory, cancel out any one person's desire to see what they want to see. And we also talked about how clinical trials are randomized and double-blind to avoid bias. These two senses of objectivity are related. The hope is that an unbiased scientific process will lead to knowledge about what the world is really like. So how is this possible? In my view, science gains some of its objectivity, in both senses of the word, by its social organization. When scientists put their minds together, when they combine their individual viewpoints, they help to rid science of bias. This is how the social structure of science, or the fact that science is conducted by communities, can help the scientific process become more objective. Let me try to further illustrate this point by telling you the classic story about the blind men and the elephant. There are many versions of this parable, all with different morals, but here's the version I like best. Long ago, a group of blind men heard that a traveler had brought a large, unusual animal, an elephant, to their village. They had heard stories about these animals, but none of them had ever met one in real life. Curious about what elephants were like, the men went to where the animal was being kept. And when they got there, they asked the traveler if they could each inspect the elephant with their hands, since they couldn't see it. The first man grasped the elephant's trunk and declared that elephants are like snakes. Another man touched the elephant's ear and claimed that the animal was like a fan. A third man petted the elephant's leg and announced that it resembled a tree, while a fourth man touched the elephant's side and claimed that it looked like a wall. A fifth grasped the elephant's tail and said that the elephant resembled a rope, and the last man felt the elephant's tusk and concluded that the animal must look like a spear. After the last man had petted the elephant, the animal grew nervous and the traveler took it away, and so the 5 men were left with very different impressions of what elephants are like. Recognizing that they had each touched different parts of the animal, they put their knowledge together to figure out what elephants are really like. And they realized that it must be a large animal with fan-like ears, tree-like legs, a snake-like trunk, a rope-like tail, and so on. Only together, not alone, could they get closer to understanding what elephants are really like. So what is the moral of this story, and what's it got to do with science? Only collectively can scientists get closer to understanding what the world is really like. They combine their subjective experiences to patch together objective knowledge of the world, and only collectively can they cancel out each other's individual biases. In our review of scientific objectivity, the first thing I want to do is clarify a simplistic picture of scientific objectivity that many people have in their heads. This is the idea that individual scientists are passive receivers of truth about the natural world, that all they need to do is follow the scientific method, and out of that pops subjective knowledge. This is just not how science works. I hope that this much has at least started to become clear to you through the course. When we analyze something philosophically, it often helps to start with a very simple formulation and then refine it. As we dig deeper into the nature of objectivity, I'm going to follow this strategy. So let's begin with a simple picture. Scientists discover facts about the world through observation, experiment, and simulation. Before critiquing this view of science or trying to make it more nuanced, I want to zero in on some of the key terms here. So first, let's talk about the term fact and the closely related terms belief and truth. Facts are true by definition. Facts are representations of how the world truly is. Now contrast this with beliefs. Beliefs can be true or false, or they can be neither. They don't by definition have to represent how the world really is. They can be wrong. They can also be about things that aren't matters of truth at all, but matters of opinion. Now, in an ideal scenario, our beliefs about the world line up with how the world truly is. And in that case, we might say that we have true beliefs about the world. In other words, beliefs that correspond to facts. So to recap, facts are what is actually true in the world. Beliefs can be about anything. They can be about facts, they can be mistaken, or they can be about opinions. And true beliefs are beliefs about facts. When we grasp the way that the world actually is, we believe the truth. But remember, we can also have mistaken or false beliefs, and sadly, all of us hold on to many false beliefs. And more importantly for this class, scientists can also have false beliefs. They can be wrong about the facts. This points to an absolutely essential and foundational principle of science. There can be a difference between what scientists believe to be true and what is actually true. Beliefs change, hopefully moving closer to the truth, but the facts remain the facts. We use scientific methods to grasp the facts, but we can be mistaken. So clearly, scientists can have mistaken or false beliefs. But one question is, can they do everything right and still have false beliefs? And this question brings us back to an idea we started with, the idea that an objective scientific process should lead to objective knowledge about the world. If we try to remove our own personal biases, are we guaranteed to have knowledge about how the world actually is? Are we guaranteed to know the facts? The answer, sadly, is no. The history of science shows us many cases where scientists made turns that we now believe are wrong. A good example of this was Einstein's false belief that the universe was static, or Hubble's inaccurate calculations about how fast the universe was expanding, both of which we talked about earlier in the course. Both of these scientists were aiming to be objective, but they still failed to produce knowledge about how the world really is. Since scientists can try to be unbiased and still sometimes fail to discover the facts, it would be better to formulate our statement of scientific objectivity in terms of aims instead of in terms of achievement. So we might say, scientists aim to discover facts about the world through observation, experiment, and simulation. This may seem like a minor change, but by adding the word aim here, we are fundamentally changing how we think about scientific success. Instead of defining success as a matter of discovering facts about the world, success becomes a matter of aiming to discover facts about the world. As a consequence, instead of thinking about scientific knowledge solely consisting of facts about the world, It's better to think about scientific knowledge as that's what's generated when scientists aim to tell us what the world is like, and not necessarily only when they do. To be clear, it's important to see that objective isn't synonymous with good and subjective with bad. We expect all kinds of judgments to be subjective. The best flavor of ice cream, whose children are most adorable, the best hockey team. These judgments wouldn't be made better if we removed our unique perspective. That's the whole point of them. Scientific investigation, however, aims to tell us the facts about the world. So scientific claims ought to be objective. This doesn't mean that scientists don't use values in their quest to learn about the world, however. They do. And some of these values actually help scientists generate knowledge. And these are what philosophers call epistemic values. So what are some of these values? Accuracy is one of them. Scientists want to make their theories make accurate predictions because that indicates when their theories are right. For example, climate scientists look at how increased greenhouse gases have warmed the planet in the past and then make predictions about how much the planet will warm if we continue to add these gases to the atmosphere. For the most part, these predictions have been accurate. The IPCC's fifth assessment report, published in 2013, looked at previous IPCC report predictions and found that, I quote, "The trend in globally average surface temperatures falls within the range of the previous IPCC projections." So this tells scientists that the theory of global warming is likely an accurate representation of what is actually going on in the world. Simplicity is another value that many scientists follow in their work. Scientists often want their theories to be simple because they think the simplest explanation is often the right one. Simplicity, or the principle of parsimony in biology, is a good example of this. It's often applied to evolutionary trees, which explain how a common ancestor evolved into a number of different species. Biologists tend to think that the tree that has the least number of branches is probably the way that speciation actually occurred. So why is this? Well, the principle of parsimony is based on another assumption, that nature aims to be efficient and economical. So we've talked about epistemic values, but I also think it should come as no surprise that scientists are human beings like everybody else, and they also hold on to other kinds of values, personal values, and biases that could negatively influence their work. In a paper she wrote about gender issues in science, the philosopher Kathleen Okreluk illustrates how this may have happened in biology. She talks about what she calls the Sleeping Beauty Prince Charming model of fertilization, which assigns a passive role to the egg and an active role to sperm, much like the traditional view of men and women. It turns out that this model might not be so correct. The egg does appear to play an active role in fertilization. How did scientists figure this out? Well, they uncovered previously ignored research that may have been ignored because of societal gender biases. So did sexism affect how biologists thought about fertilization and what research they paid attention to? It seems so, though that view did change when future generations of researchers uncovered previously ignored research. So at this point, you might be wondering, how's objectivity possible at all? As human beings, is it really possible for scientists to abandon their perspectives and their values when they enter the laboratory or the field? Well, clearly the answer is almost certainly not. The best individuals can do is try. But as many of the examples I've given illustrate, communities of individuals are another story. For the rest of this section, we're going to be talking about some of the ways that scientific communities, not individuals, can both aim to discover facts and also can aim to rid science of bias. And we're going to see that this should be viewed as a process that unfolds through time. To explain this process, I want to introduce a couple of other terms that relate to scientific objectivity, but aren't really referring to the same concept. Sometimes scientists talk about how confident or certain that they are that their theories represent how the world is. For example, in the first part of the course, we discussed the latest IPCC report, which says that scientists are virtually certain, meaning at least 99% sure, that natural causes alone cannot account for the observed global warming since 1951. But climate scientists weren't always virtually certain about this claim. As they amassed evidence, and continue to amass evidence, their confidence grew. The IPCC reports are also huge collective endeavors where thousands of scientists have critiqued each other's work and come to a consensus on what's causing global warming. Their level of consensus corresponds to a certainty about the facts, a certainty level that's been revised over time. Similar statements could be made about other examples of science we've discussed. Scientists are quite confident, but not virtually certain, that the universe is about 13 billion years old. Pinning down the exact age depends on measurements which are very hard to make, So as they continue to make these measurements, their estimates may change because the level of consensus in the scientific community may change. When scientists hold the same beliefs about how the world is, that is, when they reach consensus, it suggests that their beliefs are true and that they correspond to the facts. And the main way to get consensus is to critique each other's work, to eliminate the biases that may swing the evidence one way or the other. So finally, here's a final revision to our claim about scientific objectivity. The scientific community aims to discover facts through observation, experiment, and simulation over time. And it does this by eliminating biases through the critique and the accumulation of evidence. I think that this is an accurate and realistic statement of scientific objectivity. It makes objectivity an aim, it puts the locus of objectivity in the scientific community, and it suggests that the community has to revise its beliefs through time in order to make science better. Now, how exactly does the scientific community achieve this? That's what we'll talk about in the next part. Earlier generations of scientists and philosophers of science treated the objectivity of science as more or less a given and didn't spend a lot of time thinking about how the scientific community is organized to increase the objectivity of science. But a number of challenges to this way of thinking, some historical, some sociological, and some political, have led to a reevaluation of objectivity. And today, studying the mechanisms that foster objectivity and how they might be improved is an important and central topic for philosophers of science. So what are some of these mechanisms? It starts with how scientists design their experiments and simulations. In the last part of the course, we talked about double-blind and randomized control trials. When I say double-blind trials, this means that neither the experimenter nor the participants knows who's getting the real treatment for some illness and who's getting the placebo. So why design an experiment like this? Well, imagine you were a participant in one of the studies, and I told you were actually getting the drug treatment, not the placebo. This might influence you to think you're feeling better. Or the inverse, imagine I told you that you were getting the placebo. Maybe this would influence you to think you weren't getting any better. And the same goes for the scientists themselves. They're just as susceptible as you are to thinking that the individuals in their study who got the drug will feel better, and the ones who didn't won't. They want the drug to work, and that biases them. So what's the solution? Well, leave both the scientists and the participants in the dark. So next we get the term randomized. Randomized trials entail trying out the drug or medical treatment on half of the experimental subjects, but which half any given person is assigned to is chosen randomly. This again aims to avoid bias as much as possible. Imagine if the scientists themselves picked who's assigned to which group. Maybe without even realizing it, they might assign the healthier looking people to one group and the sicker people to the other. Wouldn't that skew the results? Well, it almost certainly would. Third, we've got the word controlled. When I say controlled trials, I mean studies that use a control group who gets the placebo, meaning they don't get any treatment. By including a group that doesn't actually get the drug treatment, scientists can figure out the effect that a drug actually had on participants. Because without it, scientists can't eliminate the possibility that just being in the trial had positive or negative effects on the participants' health. It also allows scientists to quantify the exact effect of the drug because it holds all other variables equal. The only difference between the two groups is that one group actually got the drug and the other didn't. Now, controls aren't just used in clinical trials. They're used across biology, psychology, and many other fields. More generally, we can say controls aim to eliminate the effects of what scientists call confounding variables. When you're testing to see if there's a relationship between two phenomena, a confounding variable affects the results such that it seems like that there's a relationship between whatever you're studying when there isn't. Confounding variables can also make it seem like there wasn't a relationship when in fact there was. Earlier in the course, I told you about how anytime a storm comes, I get a headache. In this scenario, the drop in barometric pressure is the confounding variable, and it makes it seem like there's a causal relationship between my headaches and storms, but there really isn't. It's really a drop in the pressure that causes both my headache and the storm. So when psychologists study how children develop a theory of mind, or the ability to describe beliefs, desires, knowledge, and intentions, they also have to use controls. So for example, in the experiment I mentioned earlier in the course, children were asked whether there was candy in the candy box or pencils. The researchers asked the children the question in different ways to limit the possibility that the way that they asked the question influenced results. And researchers also used different kinds of objects in addition to candy to again limit the possibility that the objects skewed the results. So in this way, researchers are controlling for confounding variables that they may have introduced with their experimental design. The idea is that if the researchers get the same results across all of these different variations in their experiments, then they can make a general conclusion about whether children of a certain age really can or can't attribute false beliefs to others. That is, whether or not they've developed a theory of mind. Scientists work together to design these experiments. Rarely, if ever, do they work in solitude, especially in this day and age. One scientist going it alone will probably not be able to think of as many possible confounding variables and ways to control for them as a group of scientists. So this is how, again, the social structure of the community enters into experimental design, making the scientific process more unbiased and scientific knowledge hopefully closer to the truth. In other words, making science more objective. The next mechanism I want to discuss is peer review, which I think is another centrally important way that the scientific community ensures objectivity. Peer review is the process by which scientists critique each other's work before publication. A group of scientists will first submit a paper summarizing a study that they conducted to a scientific journal, and then other researchers in their field, their peers, will deem whether or not their study is worthy of publication. So how do scientists decide this? A study might not be worthy of publication if its methodology is faulty. Say if the researchers didn't control for enough confounding variables, or if they didn't have a sample size that was sufficiently large, or if the study is riddled with statistical errors, or if they made a conclusion that their data didn't warrant. But there are also less formal ways that scientists can peer review each other's work. Before publication, scientists often present their studies at conferences. Instead of papers, they'll design maybe a poster that outlines their experiment. Their peers can then talk to them about their studies and offer advice on how to move forward. Maybe there are more appropriate statistical tests to use. Maybe there's a confounding variable that the researchers conducting the study haven't thought of yet. So peer review in all of these forms adds to the objectivity of science because it's an agreed upon mechanism for criticism. The philosopher of science Helen Longino has argued that such criticism helps scientists rid their work of biased viewpoints and as a consequence makes the scientific process more objective. So later on in the course, I'll elaborate more on Longino's work. Sometimes the publication process itself can be biased. Publishers and peer reviewers tend to prefer studies that show positive results, studies that show that there is a relationship between two phenomena. So pre-registration is another mechanism of objectivity, and it's a way for combating that particular bias. Pre-registration is a relatively new model for publishing in science. When scientists pre-register their studies, that means that they submit to a journal a detailed outline of the hypotheses they want to test in a given study and the methodologies they're going to use to test those hypotheses. Some journals will even guarantee to publish a pre-registered study regardless of the results, whether they find the effect or don't find the effect. So in this case, scientists don't have to worry about whether or not they'll get positive results. Even if their study shows no relationship between the phenomenon they're looking at, they'll still get published. So in this way, pre-registration adds to the objectivity of science by removing the incentives that currently exist for only publishing positive results. Replication is another way that the community can contribute to the objectivity of science. When scientists replicate a study, it means that they're performing a study that's already been conducted to see if they get the same results. Just in the same way, you might be more convinced that there's a relationship between the occurrence of lightning and thunder when you see this phenomena occur together time and again. Scientists might become more convinced of their findings when they can perform the same or very similar studies over and over again and still get the same results. The researchers who conduct a replication study are often different from those who conducted the original study. So in this way, replication, like peer review, is a way for scientists to check each other's work. Maybe the original group made a mistake or introduced a bias that they were unaware of, a mistake or bias that even the peer reviewers didn't catch. If this is the case, the second group of researchers probably won't be able to replicate the original study. But if they can replicate it, then that gives the whole scientific community more confidence that they are actually uncovering facts about the world. Here again, we see how the combining of different viewpoints can make the scientific process and scientific knowledge more objective. Another mechanism of objectivity I want to tell you about are meta-analyses. A meta-analysis is a statistical technique that integrates the results of many studies into one. Just as scientists are likely more objective when they function as a group, more studies grouped together have a higher probability of giving scientists an accurate picture of the world. So why is this? One key reason is that studies grouped together have more data points than the studies separately. This gives them what scientists call a higher statistical power, which means a higher probability that a study will find some effect when there's an effect to be found. In this way, one study with 100 participants might tell scientists more than 10 studies each with 10 participants. One final way that the scientific community can increase objectivity is actually in the way that credit is assigned in scientific results. The scientific community follows a funny norm. It's sometimes called the priority rule. The priority rule means whoever gets a result first, or at least who publishes a result first, is given all of the credit. This might seem strange and anti-democratic. Maybe credit should be distributed by contribution, to each according to their contribution. But in science, really, who gets there first gets all or at least the majority of the credit. And some philosophers have argued that this priority rule, the giving credit to whoever gets there first, actually encourages scientists to take risks and to investigate minority opinions or oddball ideas. Because even though most of the time the mainstream view is going to be correct, sometimes oddball, weird views are actually the ones that are correct. So if you allow the group that gets there first to get all of the credit, that's going to incentivize certain people to investigate these strange and interesting ideas. And it's also going to mean that mavericks, those that go against the orthodoxy, may have a chance of getting a lot of credit and recognition in the scientific community. So all of these are mechanisms by which the scientific community can increase the objectivity of science by working together. We've now talked about scientific objectivity, both in terms of the process of science and scientific knowledge. And we've seen that it's something that's changed over time. Although the scientific community has been wrong about the facts in the past, hopefully it's less wrong, that is, more objective today. Likewise, hopefully the scientific process itself has become less biased and thus more objective over time as well. Many early philosophers of science didn't focus on the way that science and scientific thinking has changed over time. Instead, they concentrated on analyzing what they thought was the fundamental logic of science, a logic they thought that has remained fixed over the centuries, a logic that was basically guaranteed to grant us objective knowledge. But a major change to the field was stimulated by the historian of science, Thomas Kuhn. Kuhn argued that a close examination of science's history tells us a very different story, a story rife with radical change and radical disagreement. Unlike the philosophers that came before him, Kuhn thought scientists hadn't steadily accumulated knowledge over time. Instead, he saw scientific change as cyclical, where the long-term accumulation of knowledge wasn't something that science could deliver. Over time, scientific fields cycled between what Kuhn called periods of normal science and periods of revolutionary science. During a period of normal science, researchers did accumulate knowledge by building up upon a theory or a set of theories, and these theories guided and organized their work. These theories were also accompanied by specific methods for conducting science, standards by which evidence is judged, and a general worldview or an all-encompassing picture of the way that the world is. Kuhn called this package of theory, method, standards, and worldview a paradigm. And you've probably heard the term paradigm shift before. It was Kuhn who actually popularized that term with his work. What he meant by that was that while most of science was normal science, with steady accumulation of knowledge, other times involved radical shifts. Kuhn thought that at some point, the paradigm holding research together in some field would falter. At this point, scientists would start to stumble upon a number of problems that their guiding theory couldn't explain, and where the predictions that their theories had couldn't match the observations. This would cause scientists to start to lose faith in the whole paradigm that organized their field. But not until a new paradigm came along, a theory that solved many of the problems the old paradigm couldn't solve, could scientists give up on their old paradigm. Their new theory also came with new methods, a new way of doing science, and a new worldview, which is why Kuhn argued that these scientific revolutions entail complete paradigm shifts. He saw this shift as more akin to a religious conversion experience than a rational change. His reasons for this are complicated, but the main reason is that all standards of evaluation are paradigm relative. So there's no way to objectively compare one paradigm to another. You just have to have a conversion. Kuhn was a physicist by training, so he was heavily influenced by scientific changes in that field. When he looked at the shift from Newtonian mechanics to general relativity in the early 20th century, he saw this as this kind of cyclical revolutionary change. General relativity, he thought, didn't build upon Newtonian mechanics. It provided a fundamentally different way of looking at the physical world. Kuhn thought that when Newtonian physicists used a world like space, they meant something completely different from Einstein and those that worked in general relativity. These two groups of physicists had fundamentally different standards for what counted as a solid explanation of the physical world. So in short, it was like trying to compare apples and oranges. And since it's impossible to compare the two paradigms in any sort of unbiased way, there's no perspective from which they could be compared, it was impossible to know if objective knowledge was being accumulated through scientific revolutions or through paradigm shifts. I don't agree with Kuhn about these issues. I do think that knowledge has accumulated over time. I think, in fact, there are some quite practical reasons that ultimately tell against his view. I don't think we could have cured diseases and built airplanes if knowledge hadn't been accumulating through time. But still, his arguments are very powerful, and they have to be dealt with a lot more seriously than I did just now. I also think that Kuhn did pinpoint something very important about scientific thinking that brings us back, once again, to our discussion of scientific objectivity. The scientific community is simultaneously open and resistant to fundamental changes in worldview. They'll change their mind, but there should be a really good reason for it. This balance of open-mindedness and resistance is also a sign of objectivity. My own PhD advisor, Peter Godfrey Smith, summed up this idea perfectly. He wrote, "Much of the secret of science for Kuhn is the remarkable balance it manages to strike between being too resistant to change in basic ideas and not being resistant enough. If the simplest form of empiricist thinking prevailed, people would throw ideas away too quickly when unexpected observations appeared, and chaos would result. Ideas need some protection, or they can never be properly developed. But if science was completely unresponsive to empirical failures, conceptual advance would grind to a halt. For Kuhn, science seems to get this balance just right, and this delicate balance is not something we can describe in terms of a set of explicit rules. It exists implicitly in the social structures and transmitted traditions of scientific behavior and in the quirks of the scientific mind." When Godfrey Smith mentions that this balance can't be found in explicit rules, he's talking about that fixed logic of science that many early philosophers argued made science objective. I want to talk a little more about this debate because it's an important one, and I think it will bring us back to why the scientific community is objective in virtue of scientific communities. After Kuhn's work on the cyclical nature of science, many of his peers criticized him for making science look completely irrational and subjective. One of them even said he made science a matter of mob psychology. Kuhn thought that his critics had completely misunderstood him. He said he didn't think science was completely irrational and subjective, he just thought it was more subjective than these earlier philosophers had made it out to be. So he spent much of the rest of his career responding to these critics. So remember when I talked about epistemic values like accuracy and simplicity? Well, these early philosophers of science thought that these were rules that, when applied, guided objective choices between theories. If a scientist is faced with having to decide between siding with Newtonian mechanics or siding with general relativity, she'd just figure out which theory was more accurate and simpler. Other rules she might apply would be fruitfulness, which says a theory should lead to other areas of research, or consistency, which says a theory shouldn't conflict with other theories or with itself. According to these philosophers, the rules that dictate theory choices are objective. They're part of the logic of science. And the fact that these rules dictated choice is what made scientific decision-making objective. Kuhn argued that there's lots of evidence from the history of science to suggest that these rules are more like values in the everyday practice of science. What's the difference then between logic and values? Well, rules don't leave much open to interpretation. They dictate choices. But values do leave room for subjective interpretation, and that's why they guide choices, but they don't dictate them. There's need for interpretation because sometimes scientists are put in the position of deciding between one theory that's more consistent and another theory that's more accurate and fruitful, for example. They're left to their own devices to decide which theory is better. Kuhn still didn't think science was completely subjective. He thought that the choices scientists made depended on a mix of objective and subjective factors. The scientific community did share a commitment to a number of epistemic values. This is what made science partly objective, but individual scientists were also forced to interpret how to apply these values in their everyday work. This is what made science partly subjective. So pay attention to what Kuhn is doing here. He's redefining objectivity in terms of shared values. In other words, he's redefining objectivity to mean agreement in a community. One of the last lines of Kuhn's response to his critics was this: if these criteria do not supply all the guidance that we have customarily expected of them, then it may be the meaning rather than the limits of objectivity that my argument shows. Now, Kuhn was often ambiguous in his writing, but what I think he means here is this. Maybe scientific objectivity isn't what people have thought it to be. Maybe it doesn't consist of the application of a set of rigid rules that magically prevent scientists from imputing their own personal views in their work, that allow individuals to become passive receivers of objective knowledge. Maybe, as Godfrey Smith explained, it's something that exists implicitly in the social structures and transmitted traditions of scientific behavior. Kuhn was definitely onto something here, but these ideas weren't fully fleshed out by him. Kuhn brought the social nature of science to the fore, but the philosopher Helen Longino has outlined how the social nature of science could, and I think does, ultimately make science more objective. Contrary to both Kuhn and his critics, Longino bases her argument on the idea that science literally can't be done by individuals. It can only be done by groups. Kuhn recognized that science is a social activity, but he still analyzed science on the level of the individual. He still emphasized the choices that need to be made by individual scientists. But what happens if we think about objectivity, at least in terms of the scientific process, at the level of the community? Are there ways for the community to rid itself of bias? Does the whole somehow become more than the sum of its parts? And Longino argued yes, and I agree with her. We've actually already gone over many of the ways that the community rids itself of bias, peer review being one of the main ones. Longino grouped all of these mechanisms under the heading of intersubjective criticism, criticisms for and by the scientific community. And I bring up her work again because Longino's philosophy has an important consequence. If the scientific community can become more objective, that is, less biased over time, through various mechanisms of community criticism, then that means that objectivity itself is a matter of degree. Longino went further and actually outlined 4 criteria she thinks can be used to figure out how objective the scientific process is at any point in time. The first of these is recognize avenues for criticism, avenues like peer review, conferences, replication, and the like. And on this note, Longino argues that scientists should get equal credit for participating in these avenues of criticism as they do for generating original research. This would be quite a radical change to the scientific community. The second was shared standards of values, such as accuracy, consistency, and simplicity, much like the list that Kuhn outlined. But Longino added an idea that Kuhn would probably have agreed with, but didn't make explicit. It's that the existence of shared standards that makes individual members of a scientific community responsible to something besides themselves. A third criterion for evaluating objectivity, according to Longino, is community response to criticism. It's one thing to advance a criticism, but if nothing changes in response to that criticism, then what's the point of it? What's the point of having those avenues to begin with? There should at least be some kind of counter-argument offered to argue that the criticism is unwarranted. And this happens all the time in peer review. For example, a peer reviewer might criticize a study on some point, say, why did they use this statistical technique instead of another? And the researchers might convince the reviewer that what they did was fine after all. So we'll come back to this idea in the next part of the course when we address failures of objectivity. There are reasons to doubt whether the scientific community always responds to criticism in an adequate manner. Without going yet into much detail, I can bring up one example. So at one point in time, it didn't seem like researchers got equal credit for doing replication studies. However, there have been recent efforts to change that, and in certain fields, it's becoming a high-status, high-profile activity to do a replication study. Longino's final criterion is what she calls intellectual authority. Generally, this means that the scientific community shouldn't exclude certain viewpoints for political reasons. A great example of this is the early 20th century Soviet Union. In the early 20th century, the Soviet biologist Lysenko led a political campaign that was supported by Joseph Stalin to jail and even execute biologists who supported Darwin's theory of natural selection. Lysenko supported an alternative view of evolution that rejected the idea of genes and claimed that traits acquired in the lifetime of an organism were inherited. But there are other ways the scientific community can violate this criterion that may hit closer to home. Longino argues that the historical exclusion of women and minorities in the sciences made sciences less objective. This is still a problem today, though one can argue that it's at least been improved since the days of Newton and Darwin. In the next part of this course, I want to take a closer look at these issues and others. But before wrapping up, I want to make one final point. While I mostly agree with Longino's analysis of the objectivity of the scientific process, I also think a similar argument can be made for the objectivity of scientific knowledge. I do think that the scientific process is becoming more objective over time, that is, less biased. But I also think that scientific knowledge has more truthfully and thus more objectively portrayed the world over time as well. And my reason for saying this returns to the story of the blind man and the elephant, and my repeated emphasis on the role of the scientific community. Each individual in a community is no doubt biased in some way or other, but by organizing so that knowledge is shared, norms of truthfulness are enforced, and results are subjected to scrutiny, our beliefs about the world can come closer to the truth. This is how the scientific community can work towards the goal of producing objective knowledge, but they have to do it together. In 1998, medical researchers in the United Kingdom published a study in The Lancet, a well-respected scientific journal, that claimed to find a link between the measles, mumps, and rubella vaccine and autism, a developmental disorder. Shortly after the study was published, other medical researchers pointed out its many flaws. For one, the sample size of the study was only 12 children. The study also didn't include any controls, so the paper provided insufficient evidence to support its conclusion that there's a link between the MMR vaccine and autism. But the public didn't hear or didn't listen to the criticisms of the wider scientific community. Following the study's publication, MMR vaccination rates fell across England and Wales, leading to a sharp rise in confirmed cases of measles, from 56 in 1998 to a peak of 2,030 in 2012. The region also saw an increase in confirmed cases of mumps, from 121 cases in 1998 to over 43,000 in 2005. The number of confirmed cases of measles and mumps has declined since 2012 and 2005, but still too many people in the UK, the US, and elsewhere think that there might be a link between vaccines and autism. People including President Donald Trump and actor Jim Carrey and countless websites continue to spread the doubly bogus claim that the autism epidemic is real and excessive vaccinations are the cause, all because of one faulty paper. In 2004, the Institute of Medicine of the National Academies published a report that concluded the body of epidemiological evidence favors rejection of causal relationships between the MMR vaccine and autism. Evidence also suggests that there hasn't been an actual increase in autism spectrum disorder. The increase in reported cases has likely been caused by greater diagnosis efforts and a broader definition of the disorder than an actual increase in children with autism. Let me be clear, the 1998 study is not objective science. Faulty study design was only one of the many failures on the part of the researchers who conducted that study. In 2004, Brian Deer, a journalist at the UK's Sunday Times, reported the study's data was potentially fraudulent, which led Britain's General Medical Council to start investigating the case. Together, Deer and the council showed that the children's medical records and the parents' testimony didn't match what was reported in the paper. For example, some of the children experienced symptoms of autism before they received the MMR vaccine, but the paper didn't say that. And finally, in February of 2010, over a decade after its publication, The Lancet formally retracted the paper. When a journal retracts a paper, it means it's removing it from the public record, from the body of work scientists have been creating for centuries. But the story still doesn't end here. A few months later, in May 2010, the General Medical Council banned the lead author of the study, Andrew Wakefield, from practicing medicine in Britain, though he had already left the country in 2004 for Texas, where he had set up a practice without a US medical license. Overall, the council brought more than 30 charges against Wakefield. This included taking money from lawyers who had represented parents who were suing vaccine makers. This suggests he had a clear bias to find a link between vaccines and autism. They also charged Wakefield with carrying out invasive and unnecessary medical procedures on children and collecting blood samples for research from children at his son's birthday party. Both of these are highly unethical. The council banned one of Wakefield's co-authors, John Walker Smith, from medical practice for similar misconduct as well. You might be wondering why I'm telling you this story, especially after we've learned about the many ways that scientists strive to keep their work objective. But as I mentioned in the very first week of this course, the scientific community does have limitations. Like any human endeavor, scientific research can go wrong, and in this case, very wrong. Now, this isn't the only case of science going wrong, and in this section of the course, we're going to go over the ways that scientists can fail to produce objective science. It will help to organize our thinking to consider a range of ways that things can go wrong, from honest mistakes to outright fraud. Let's begin with the least scandalous example of the bunch, honest mistakes. In 2016, Maureen Gannon and Raymond Pasek, researchers at Vanderbilt University, asked the American Journal of Physiology, Endocrinology, and Metabolism to retract one of their papers because they realized they had been studying the wrong line of transgenic mice. The mix-up invalidated the results of their study, and in an interview, the researchers told Retraction Watch, which monitors scientific retractions, why they decided to retract their own paper. They said, "Honesty is always the best policy, even if it's hard, especially in today's climate of fake news and science being under attack. The scientific community and the public needs to trust published scientific results. We should be able to admit when a mistake is made and correct the literature. This has been a learning experience for us and an opportunity for growth." So compared to the vaccine autism example, how does this example change the way you see science? You might have lost some faith in science with the Wakefield case, but does this example have the same effect? Hopefully the answer is no. Some might think of Gannon and Pasek's case as an example of science gone wrong, but I actually think it's an example of science gone right. There was an error, and it was corrected. So on one end of the spectrum, we've got Gannon and Pasek's case, and on the other end, we've got Wakefield's case. But there's a lot in between. So let's take another example involving peer review. I've already introduced you to the practice of peer review, but to remind you, it's a stage in the publication process where researchers will evaluate the merit of a study that they haven't participated in. Sometimes peer reviewers deem a study unpublishable. Sometimes they suggest edits, and sometimes, though rarely, they accept it outright. Often the researchers who did conduct the study suggest potential peer reviewers to journal editors. In 2012, an editor at the Journal of Enzyme Inhibition and Medicinal Chemistry was puzzled when the reviews for a study by Hyung-In Moon, a medicinal plant researcher then at Dongguk University in South Korea, came back within 24 hours. Usually it takes much longer because reviewers aren't paid for this work and they have to fit the reviews into their already jam-packed schedules. When the editor confronted Moon, Moon confessed that he had written the reviews himself. Moon had given the editor the names of real scientists as suggested reviewers, but fake email addresses that went to his inbox. His admission led to the retraction of not one, but 28 papers. But while Moon's case is extremely rare, it's not unique. In fact, just last year, the journal Tumor Biology retracted a record 107 papers in just one day because they had all been reviewed by researchers who had conducted the studies. All right, so this is obviously a much larger failure in objectivity than Gannon and Pasek's simple mistake. Given the extent of the failure, it would be understandable if this caused you to see science as broken. But again, I'll reiterate that it's actually an example of science's self-correcting nature. The problems were found and they were rectified. Now, another issue plagues science that's even more widespread than fake peer review, and it's called p-hacking. To explain this phenomenon, I first have to explain what a p-value is, which is what the p in p-hacking refers to. A p-value is a statistical measure that guides scientists in determining whether they can reject their experiment's null hypothesis. Generally, a null hypothesis says that there is no difference between the experimental group and the control group. So here's an example to clarify what this means. Imagine a scientist who wants to test whether a drug she's just developed actually does what it's designed to do, let's say reduce nausea. She would give the drug to, let's say, 100 people and give a placebo to another 100 people. The experiment's null hypothesis would predict that as a whole, the people who took the drug and those who took the placebo would experience the same amount of nausea, meaning that her drug didn't make a difference. Now, in a typical study, two things would have to be evaluated. First, the researcher would look to see if there is some measurable difference between the two groups. And second, a statistical analysis of this difference would have to produce a small p-value. Less than 0.05 is the norm. A p-value of 0.05 means that there's a 5% chance that the measured difference could be the result of chance alone. And if it were the result of chance alone, then rejecting the null hypothesis in favor of the test hypothesis would be an error. It would be a false positive result. Why 0.05? Statistics can't provide certainty that the null hypothesis was rejected in error, so scientists as a group have agreed that 95% confidence is sufficient. More generally, the lower the p-value, the less likely the null hypothesis would be rejected by chance alone. So journals tend to publish papers that find positive effects and rarely publish studies that don't reject the null hypothesis. So as a result, researchers are more likely to get published if they do experiments that find positive effects than experiments that find no effects. So this is where p-hacking comes in. In order to get published, scientists will collect lots of different types of data and then try out many different kinds of analyses in order to find out one that does produce positive effects. Many argue that this practice, which occurs especially in the life and social sciences, has led to false positive results, meaning that the study suggests there's an effect, but there really isn't. And the reason is that if the community is willing to accept a 5% false positive rate in any one test, doing many different tests of different correlations is eventually going to lead to some false positives getting published. A related kind of p-hacking is sometimes called the file drawer or trash can problem. Since journals generally don't publish negative results, it's impossible to get a real sense of the balance of evidence from the published literature. Imagine an important correlation was investigated 10 times. And let's say that out of the 10, only 4 times the correlation was actually observed. Well, if journals mostly want to publish positive results, only these 4 positive, or maybe the 4 plus 1 negative, will get published. So if someone's looking in the literature, they might think that the correlation is very robust, when in fact it isn't. Some argue that p-hacking has led to a replication crisis in the life and social sciences. So replication is an important part of science when researchers conduct the same or a similar experiment multiple times and they see the same or similar results. When they do this, they might know they're really onto something. But if p-hacking leads to false positives, then those studies won't be able to be replicated. Some argue that p-hacking has led many published studies to be false, but others have said that, well, it probably does skew the body of science towards inaccurate results, the effect is overblown. Regardless, the problem at least partially lies in the publishing world, and some researchers who act as journal editors are seeking to change this publishing culture. For example, some journals now offer a new route to paper publication called pre-registration. With pre-registration, researchers submit a detailed methodology of their experiment, and their study is accepted regardless of the results. I could see how the possibility of widespread false positive results might make you lose some respect for science, but it wouldn't be the first time that science has taken a wrong turn on a massive scale. For example, in the 18th century, many chemists thought that when a substance burns or rusts, it loses an element called phlogiston. Now researchers know that burning or rusting are a process that actually adds an element, oxygen, to the substance. This is one of the many wrong turns science has made in the past, which has now been corrected. So now it might not seem like the example of phlogiston is anything like p-hacking, but here's what ties them together. They both embody a fundamental quality of scientific progress, that at any given time, the body of scientific evidence will include some false conclusions. But over time, as scientists pick apart each other's work, mistakes, both ethical and empirical, are corrected, even as other different mistakes are being made. So in the words of Brian Nosek, another researcher who's striving to fix problems like p-hacking, the goal of science isn't to produce 100% truth, it's to get less wrong over time. Wakefield's autism research case brings up one last topic I'd like to touch upon. Whether or not research from specific sources should be trusted, such as the industry or government. Wakefield was paid by lawyers who were suing vaccine companies on behalf of parents who said vaccines harmed their children. Intuitively, we wouldn't want to trust his research because that exchange of money suggests he's not going to perform honest research. That's why pretty much every scientific paper that's published in a reputable journal now includes financial disclosure information. Researchers have to sign forms stating that they have no conflicts of interest, financial or otherwise, when they publish their work. Now, this isn't to say that all research that's funded by industry, let's say, is faulty, nor is all research funded by the government faulty. This is a case where you have to approach the source of information with a critical eye. Does the source have a motivation to give the result that it has? Has the information been independently reviewed? Has it been confirmed by other studies led by other groups? One of the reasons why huge international consortia, such as the Intergovernmental Panel on Climate Change, were formed is precisely to address these issues. Now that we've gone through all of these examples, you might be wondering how all of these can be squared with the image of science we began with. Either consciously or subconsciously, we might have thought that science was purely objective and rational, yet many of the actions of scientists in the previous examples don't seem to be. So you might be asking, can we trust science? And how can we even tell the difference between objective science and fake science? In the next part, I want to dive into how philosophers have answered these questions. So what makes science science? This is one of the most important questions in the philosophy of science, in part because it doesn't just reside in the halls of academia. It also permeates society at large, making its way into decisions of our courts, the rhetoric of our politicians, and the marketing of our food. Being able to distinguish non-science, or what philosophers call pseudoscience, from science can help us as citizens of the information age navigate the many claims that are thrown at us every day. One of the most influential philosophers to address this question was Karl Popper. Popper grew up in Vienna in the early 20th century when the city was overflowing with new and exciting philosophical and scientific ideas. Some of these ideas came out of what's now known as the Vienna Circle, a group of philosophers and scientists, including Moritz Schlick and Rudolf Carnap, who arguably laid the foundation for modern philosophical analysis of science. As a student, the young Popper was lucky enough to attend a lecture by Albert Einstein on his relativity theory. He also got involved in left-wing politics, becoming a follower of Karl Marx. And in his early years, Popper actually studied psychology, not philosophy, and during this he studied and was exposed to the theories of Sigmund Freud and Alfred Adler. All of these thinkers greatly influenced Popper's solution to what philosophers call the problem of demarcation, the difference between what's science and what's pseudoscience. Popper grappled with this problem for his entire career, but his solution was always grounded in the idea of falsification. In other words, according to Popper, scientific theories can be falsified, while pseudoscientific theories cannot be. One of his best explanations came in a lecture he gave at Cambridge University in the summer of 1953. So in that lecture, Popper starts by asking his audience, is there a criterion for the scientific character or status of a theory? Popper explains that this question isn't asking when a theory is true or acceptable. Instead, he says, he wished to distinguish between science and pseudoscience, knowing very well that science often errs and pseudoscience may happen to stumble upon the truth. Popper points out that others have tried to solve this issue, but in his opinion, unsatisfactorily. One of these solutions, known as the verifiability criterion, came out of the Vienna Circle. According to Carnap and Schlick, what makes a statement scientific is if, at least in principle, it's able to be verified. This is another way of saying that these statements are based on observation. As we've already discussed, observation is a central and important part of what makes science science, but Popper argued it's not enough to distinguish science from pseudoscience. He gives the example of astrology, with its stupendous mass of empirical evidence based on observation, on horoscopes and biographies. Popper, and I don't think he's alone, doesn't want to give astrology the title of being scientific, yet it would fulfill the verifiability criterion. But Popper says his analysis of astrology wasn't what ultimately led him to his criterion of falsifiability. It was actually Einstein's theory of relativity, Marx's theory of history, and Freud's psychoanalysis. Even in his youth, Popper sensed that there was something that distinguished Einstein's theory from those of Marx and Freud. But it wasn't the truth of Einstein's theory. Popper actually readily admits that back in 1920s, he wouldn't have felt confident saying Einstein's theory was true. There just wasn't enough evidence at the time supporting it. So truth wasn't the metric he felt distinguished science from pseudoscience. With time, Popper realized that it was Einstein's ready acceptance of the possibility that his theory could be falsified in light of new evidence that made it scientific, while the theories of Marx and Freud took any evidence whatsoever as confirmatory. Popper explains how in the following passage. These theories appeared to be able to explain practically everything that happened within the field to which they referred. The study of any of them seemed to have the effect of an intellectual conversion or revelation, opening your eyes to a new truth hidden from those not yet initiated. Once your eyes were thus open, you saw confirming instances everywhere. The world was full of verifications of the theory. A Marxist, for example, could not open a newspaper without finding on every page confirming evidence for the political philosopher's theory of history, which says that all capitalist societies will evolve into communist ones because the working class will revolt against the wealthy. Likewise, the Freudian analysts claimed that their theories, which emphasized the unconscious drives and instincts of the mind, were constantly verified by their clinical observations. Popper was actually lucky enough to correspond directly with Adler, who claimed that the main driver of human thought and action was actually an individual's desire for superiority as a reaction to feelings of inferiority. Popper tells us about a point in 1919 when he had told Adler about the case of a child which, to Popper, didn't seem to fit the theory. Yet Adler found no difficulty in analyzing this child in terms of his theory of inferiority feelings. And Popper was surprised because Adler hadn't even seen this child. Now, with all of these cases, Popper's pointing to a phenomenon we now call confirmation bias, or our propensity as humans to see new evidence as confirmation of the beliefs or theories we already hold. Popper illustrates this point by comparing two men, one who attempts to drown a child with another who sacrifices his life in an attempt to save a child. Popper looks at these cases and says both of them are explained by both the theory of Freud and of Adler. Freud would say the first man suffered repression, and the second had transformed his socially frowned upon impulses into socially acceptable ones. Adler, on the other hand, would say that both men suffered from feelings of inferiority, but just reacted to those feelings in different ways. So, in thinking about these cases, Popper concludes it was precisely this fact, that they always fitted, that they were always confirmed, which in the eyes of their admirers constituted the strongest argument in favor of these theories, but it began to dawn on me that this apparent strength was in fact their weakness. But with Einstein's theory, it was strikingly different, Popper argued. Einstein's theory of general relativity made the risky prediction that light rays from faraway stars would be literally bent by the gravitational field of the sun. The prediction was risky, says Popper, because it contradicted the views of pretty much all of the scientists at the time. But in 1919, the British astronomer Arthur Eddington took a photo during a solar eclipse that showed exactly what Einstein predicted. If the photo had shown the opposite, that the star's light rays hadn't been bent by the sun's gravity, Einstein's theory would have been simply refuted. And closer to our own time, the shadow of a black hole was imaged. Black holes are one of the weirder predictions of Einstein's theory, and yet the recent image of a black hole's shadow, as well as the ripples through space-time recorded when two black holes collided, provides striking predictions that are consistent in detail with Einstein's theory and could very easily have falsified the theory. In other words, Einstein's theory is incompatible with certain possible observations, Popper wrote. And this is in contrast to the theories of Marx, Freud, and Adler, which proponents reason can be compatible with pretty much any observation you throw at them. All of this can be boiled down to the following list. It's easy to come up with confirmations of theories, especially when we're actively looking for them. A theory that can't rule out any phenomenon isn't scientific. And the more a theory rules out with its predictions, the better it is. In a nutshell, the criterion for scientific status of a theory is falsifiability. So Einstein's theory of general relativity would count as scientific, while those of Freud and Adler and Marx would be pseudoscientific. Now, I should say that Popper was especially radical about this point. He thought that not only was falsifiability the criterion for good science, all scientists could ever try to do was to falsify their theories. This latter point has nearly been universally rejected. Probably more than any other philosopher's method of demarcation, Popper's falsifiability criterion has permeated public discussion about science. So in 2016, for example, when he was running for president, Texas Senator Ted Cruz used it to falsely claim climate science was pseudoscientific. So Senator Cruz said, if you're a big government politician, if you want more power, climate change is the perfect pseudoscientific theory. How many of y'all remember high school biology? Remember this scientific method? You start with a hypothesis and then you use evidence to try to disprove the hypothesis to test if it's true. Climate change is the perfect pseudoscientific theory because it can never, ever, ever be disproven. If it gets hotter or colder, wetter or drier, the climate has always changed since the beginning of time. It will continue to change till the end of time. But here's the thing. The theory of climate change could lose scientific support if observations started to not match what the theory predicts. Climate scientists can and do point to a number of ways that climate change could lose support. For example, the climatologist and geophysicist Michael Mann told a reporter at factcheck.org, a nonprofit run out of the Annenberg Public Policy Center here at Penn, that if scientists found strong evidence to suggest that gases like carbon dioxide don't actually trap the sun's heat, it would radically alter the view of climate change. In other words, if scientists lost confidence in the theory of the greenhouse effect, it would affect how much support they have for the larger theory of climate change. Likewise, if scientists found strong evidence to suggest that global warming isn't the result of increased levels of greenhouse gases, they'd also lose confidence in the theory of climate change. Or if they found that the planet hadn't warmed as much as scientists thought it had, or will, this would also give them reason to reevaluate the theory. But the predictions of climate scientists have so far matched observations. For example, the United Nations Intergovernmental Panel of Climate Change's fifth assessment report, published in 2013, took a look at previous IPCC reports, and they found that the trend in globally average surface temperature falls within the range of the previous IPCC projections. There's also strong evidence to suggest that climate change has and will continue to make certain parts of the world wetter and other parts drier. Heat turns ice into water and water into water vapor, so in regions with glacial mountains, global warming may lead to more flooding, whereas in areas with lakes or moist soil, global warming could lead to more drought. Climate change isn't the only scientific theory that's been deemed pseudoscientific by its critics. Evolution's another. Some of these claims have occurred in the context of court cases on whether evolution, as opposed to some form of creation, should be taught in public schools. The legal debate dates back to 1925 when Tennessee authorities arrested John Scopes, a substitute high school teacher, for teaching Darwin's theory of natural selection. Why exactly was he arrested? Just a few months earlier, the state's legislature had passed the Butler Act, introduced by Tennessee Congressman John Washington Butler, which prohibited teaching any theory that denies the story of the divine creation of man as taught in the Bible, and to teach instead that man had descended from a lower order of animals. The act, which applied to any public school including universities, specifically prohibited the teaching of evolution theory. During the Scopes trial, also known as the Monkey Trial, Judge John Tate Ralston ruled out any testimony from scientists on the validity of Darwin's theory, as well as any discussion of whether the Butler Act was constitutional. Scopes was found guilty and fined $100, which is about $1,400 today. When Scopes appealed the decision, the state Supreme Court upheld the constitutionality of the Butler Act, but still acquitted Scopes because they deemed the $100 fine excessive. The act wasn't deemed unconstitutional and repealed until 1967, when another teacher, Gary Scott, challenged the state in court. This ruling was followed up by similar ones in Arkansas and Mississippi, which at that point were the only states to still have bans on evolution teaching on their books. But attacks on the teaching of evolution in public schools didn't end there. The 1980s case, McLean versus Arkansas, concerned the constitutionality of Act 590, which was put into law in 1981. The act mandated that public schools in Arkansas shall give balanced treatment to creation science and evolution science. Ultimately, Judge William R. Overton ruled that the act, among other things, violated the Establishment Clause of the First Amendment, which says that Congress, both federal and state, shall make no law respecting an establishment of religion. This means that the government can't pass laws that favor in any way one religion over another, or even favor all religions. In his memorandum opinion, or ruling, Overton concluded that the evidence is overwhelming that both the purpose and the effect of Act 590 is the advancement of religion in public schools. Now, Overton provides an interesting history of the debate between creation science and evolution over the decades. The concept of creation science, or that divine creation of life is backed by scientific evidence, was actually a response to the modernization of the teaching of science in public schools in the 1950s and 60s. This curriculum change included integrating the theory of evolution as a central theme in biology textbooks. Creationists, on the other hand, view evolution as the source of society's ills, he wrote, and he cites a passage from the 1976 book, The Bible Has the Answer, in which the authors claim that evolution is utterly unscientific and has served effectively as the pseudoscientific basis of atheism, agnosticism, socialism, fascism, and numerous other false and dangerous philosophies over the past centuries. For this reason, a large chunk of Judge Overton's opinion evaluated the scientific merits of creation science and evolution. If creation science could in some way be deemed science and not an appeal to religion, then the logic went it wouldn't violate the Establishment Clause. Or alternatively, if evolution could be deemed pseudoscientific, perhaps it would be banned from schools. Sorting all this out entailed having to define what science is and what it isn't. And based on witness testimony from scientists and philosophers, Overton listed essential characteristics of science, which included falsifiability, testability, and tentative conclusions. Overton argued that creation science is simply not science because it meets none of these characteristics. Let me quote his decision. A scientific theory must be tentative and always subject to revision or abandonment in light of facts that are inconsistent with or falsify the theory. The creationists' methods do not take data, weigh it against the opposing scientific data, and therefore reach the conclusions. Instead, they take the literal wording of the Book of Genesis and attempt to find scientific support for it. While anybody is free to approach a scientific inquiry in any fashion they choose, they cannot properly describe the methodology as scientific if they start with the conclusion and refuse to change it regardless of the evidence developed during the course of the investigation. In short, creation science is pseudoscientific, at least as Popper defines it. It takes any evidence whatsoever as confirmatory evidence. Well, what about evolution? Overton doesn't directly evaluate whether or not Darwin's theory of natural selection is scientific or pseudoscientific. The Act 590, however, did claim that evolution science is not an unquestionable fact of science because evolution cannot be experimentally observed, fully verified, or logically falsified, and because evolution science is not accepted by some scientists. The Act also equates belief in evolution with a religious belief, and thus teaching it in schools violates the Establishment Clause of the First Amendment. So is evolution not science but religion? In other words, can it be falsified? Well, Popper himself said that it was difficult to falsify, though he did deem it science. But other philosophers have argued that the difficulty of falsifying aspects of the theory of evolution have more to do with problems with Popper's rule of falsification and less to do with their theory of evolution. One of these philosophers is Philip Kitcher. And Kitcher's argued that the way to begin thinking about creationism and pseudoscience is by starting from noting that nothing in science is an unquestionable fact. In other words, nothing is certain, so criticizing evolution on this point is a false start. In a chapter of his 1982 book, Abusing Science, The Case Against Creationism, Kitcher argues that complete certainty in science is best seen as an ideal towards which we strive, and that's rarely, if ever, attained. Instead, he says, fallibility is the hallmark of science. By this, Kitcher means that no scientific ideas are ever certain. All of them are revisable. Still, he says, to concede that evolutionary biology is a theory is not to suppose that there are alternatives to it that are equally worthy of a place in our curriculum. All theories are revisable, but not all theories are equal. Now, this might sound like it agrees exactly with Popper's falsification criterion for distinguishing science from pseudoscience, but it doesn't. And here's why. According to Kitcher, falsification either debars most of what we take to be science from counting as science, or it allows virtually anything to count. To illustrate that falsification could exclude most of what we consider to be science, Kitcher points to Newtonian mechanics, which he defines as Newton's 3 laws of motion and his law of gravity. Kitcher says, suppose that when an apple falls from a tree, it doesn't fall to the ground as predicted by Newton's law. Would that mean we have to abandon Newton's time-tested theory? No, of course not. We could always say that some other force was at work that prevented gravity from taking hold of the apple and saved the law of gravity from falsification. And we could do the same with pretty much any scientific theory. That means that all of science is actually unfalsifiable by Popper's narrow criteria. So we begin to see why Kitcher, as well as many other philosophers of science, have argued that there's something fundamentally wrong with relying solely on Popper's criterion of falsifiability to determine what's science and what's not. Now, to give Popper the benefit of the doubt, Kitcher says perhaps equating Newtonian mechanics with Newton's famous 4 laws was the problem. It wasn't Popper's narrow criterion of falsification. Suppose then that we define Newtonian mechanics to include those 4 laws, but also to include supplementary assumptions that allow for specific observations and thus to be falsifiable. This remedy fails, says Kitcher. This way of changing Popper's theory would fail because it could still allow anything to count as science. To illustrate this point, Kitcher gives an amusing example of an overpaid spiritual teacher who makes the bold claim that quietness is wholeness in the center of stillness. Suppose we point out to that teacher that his central message is unfalsifiable. The teacher could easily argue that his doctrine does make predictions. Maybe that flowers bloom in spring and that bees gather pollen. So if flowers bloom in spring and bees gather pollen, then quietness is wholeness in the center of stillness. In short, this means that any statement could be coupled with other statements to predict specific observations. To return back to the debate between creationism and evolution, Kitcher concludes that sure, creationists can use Popper's criterion of falsification to try to show that evolution is not science, but the point is that Popper's criterion can be used to show that nothing's science, or that everything is, so something must be wrong here. Kitcher builds his account about how we should distinguish science from pseudoscience by looking at a classic example from the history of science, the discovery of Neptune. Using Newtonian mechanics, scientists, or what were then called natural philosophers, were able to predict the orbits of most of the planets in our solar system very, very precisely, all except for Uranus. By the early 19th century, it was clear that scientists either had to abandon Newtonian mechanics, at least as it applied to orbits of the planets in our solar system, or something was specifically wrong with Uranus. The most avid followers of Popper's criterion of falsification might have said that natural philosophers at this point should have abandoned Newtonian mechanics because it was making false predictions. But the more sensible reaction, says Kitcher, is to ask what made Uranus's orbit so difficult to predict. And that's exactly what astronomers did. They posited that there was possibly another planet beyond Uranus that was affecting its orbit. So they computed the orbit of this postulated planet and showed that the inconsistencies of the motion of Uranus could be explained by this missing planet's orbit. Astronomers then began to look for this new planet, and in no time, they found the planet Neptune. Now, there are three morals from this story, says Kitcher. First, in order for science to be science, what Kitcher calls auxiliary hypotheses, in this case, the hypothesis that there's another planet beyond Uranus, need to be independently tested. So you can't just say, for example, that unanswered questions in evolutionary science are evidence for creationism, as many creationists do. Much in the same way that you can't say that the anomalous motion of Uranus was the evidence for Neptune's existence. The existence of Neptune had to be independently tested, and so too must hypotheses posited under creationism. The second moral, says Kitcher, is that science should be unified, or as he puts it, a thriving science is not a gerrymandered patchwork, but a coherent whole. Good theories consist of just one problem-solving strategy or a small family of problem-solving strategies that can be applied to a wide range of problems. And the third moral is that theories in science should be fruitful. That is, they should open up new areas of research. So using these criteria, Kitcher replaces the simplistic falsification method of determining science from pseudoscience with what he calls a battery of tests, these three criteria with which to distinguish science from pseudoscience. Finally, Kitcher argues that scientific research programs are fecund. They are productive and produce new results. They respond to objections, and they have standard outputs such as papers, books, and maybe even technological products. So for Kitcher, we discover that a science is genuine not by asking if its theories are falsifiable, but by looking at how the research community is behaving. We have covered a lot of ground discussing scientific objectivity and failures of objectivity. I hope to have convinced you that a centrally important goal of scientific inquiry is objectivity. Individuals can fall short of this goal, as can communities, but by arranging scientists to work in communities, the community comes to be more objective, uncovering errors, uncovering bias, uncovering outright fraud, and aligning our beliefs with facts. In other words, the scientific community can produce objective scientific knowledge. Last week we talked about times when science fails to be objective. We looked at some clear cases where bias hinders scientific progress, when scientists take money from industry in exchange for skewing their results, when they cheat peer review by posing as reviewers, when they p-hack. But we also looked at how the scientific community has mechanisms to counteract these kinds of biases. This week I want to talk about a related topic, how values enter the scientific enterprise. When scientists enter their laboratories or go observing in the field, should they set aside their personal moral and political values, or can these values be fruitfully incorporated into their research? Do value judgments conflict with scientific objectivity? Does science itself have a value system? And how should the scientific community respond to those who challenge or reject it? To ease our way into these topics, let's return again to Clinton's speech at the Democratic National Convention and the science marches that followed. Clearly, this involved making a particular value judgment explicit. Scientific inquiry, indeed the production of knowledge in all of its forms, is worth a political fight. It's one thing for a politician to say this, but how about individual scientists or scientific organizations? Does it defy scientific objectivity to value, perhaps even to fight for science itself? Let's think about the Marches for Science. In these protests, scientists marched alongside members of the public. The point of these marches wasn't just to promote science. There's a reason why they were set up in the first place, to fight back against perceived attacks on science, particularly climate science. It wasn't a coincidence that the first march took place on Earth Day, nor was it a coincidence that it took place right after the election of Donald Trump, who has said that climate change is a hoax. Now, numerous scientific organizations, including the American Association for the Advancement of Science, have supported the marches. So they clearly have some sanction within the organized scientific community. But other scientists were opposed. Writing in the New York Times op-ed section, geologist Robert Young said that he feared the March for Science will serve only to reinforce the narrative from skeptical conservatives that scientists are an interest group and politicize their data, research, and findings for their own ends. So there is clearly disagreement in the scientific community about how much scientists should get involved in politics and other matters of value. I think that this disagreement goes back to some traditional debates about the relationship between facts and values. To begin looking more seriously at the role of values in science, I want to introduce a traditional philosophical distinction, the distinction between facts and values. In our discussions about objectivity, I said that facts are what is actually the case in the world and that true beliefs are beliefs about facts. We have true beliefs when we grasp the way that the world actually is. Now, value is what philosophers call a normative term. It describes a judgment about how something ought to be. When we're talking about values in this context, we are typically talking about judgments about what is good and bad. So it's a fact that the climate is warming rapidly due to greenhouse gas emissions, but it's a value judgment that this is a bad thing. When a politician argues that regulatory decisions, including where we should get our energy, should be made on scientific grounds, that's also a value judgment. Now, some might judge science to be our best means to a good future, but others might judge, and in fact do judge, otherwise. Those marching for science do think that science should guide our regulatory decisions. They think that not only should science be free of political meddling, but that it should play a central role in making decisions about how to run our country. When Clinton said, "I believe in science," what she implied is that we shouldn't use our judgment of political expediency to challenge the findings of science. Instead, we should have our policies guided by science. Now, Clinton is clearly making a value judgment, and this value judgment wasn't derived from science. She was stating her belief that a rational society lets its policies be guided by science. Societal values should be guided by science. The question for us to consider this week is the opposite of what Clinton was talking about. Should scientists ever be guided by values? Should what they consider to be good, just, or even expedient be a factor in the experiments they perform, the conclusions they draw, or the theories that they endorse? There's a traditional view that emphatically says no. Science and values are entirely separate domains, and science should keep itself independent of values. Philosophers have called this view the value-free ideal. Now, proponents of the value-free ideal reason like this. They say that science is about finding out what the world is like, independently of what you, me, or anyone else thinks about it. We ask questions, and the world answers those questions. While there can be disagreement about what the world is saying as we conduct our observations, our simulations, and our experiments, ultimately, there is a right answer to be found, and the right answer is settled by what the world is like alone. But what scientists think is good is, of course, a different beast. We can all be perfectly well acquainted with the same facts, yet have different ideas about what is good. This is because in our personal value systems, or our culture or our religious systems, we put different weights on different values. It can be perfectly reasonable to disagree about what is good. Science is different. True beliefs about facts are settled by what the world is like. Science shouldn't have the property that different people could rationally have different true beliefs. We can be uncertain or we can be wrong, but there's ultimately a single correct answer. Moreover, the argument goes, if we want science to help guide our decisions, we want the outputs of science to be value-free. Figuring out the best action to take requires combining what scientists tell us about the world with what we want to happen. And we're better able to bring about what we want to happen the more we know what the world is like. So the value-free ideal is the traditional view, but is it the correct view? Several philosophers have thought not. They argue that when you look closely at scientific practice, you will see that judgments about facts and judgments about value intertwine. Sometimes this is overt, but other times it's very subtle. It's easiest to illustrate this challenge when we consider very extreme cases of values, including terrible ones, influencing science. So let me give you an example of just such a terrible case. Philadelphia physician and physical anthropologist Samuel Morton was a major scientific figure in the 19th century. Among his more notorious achievements was the publication of a series of works that claimed to demonstrate the superiority of Europeans on the basis of measurements of cranial capacity, a proxy for brain size. His work had tragic repercussions. It was used as a scientific basis for the Southern American Jim Crow laws, which entrenched racial segregation in the late 19th and early 20th centuries. But for our purposes, the central issue is one of value. Morton was clearly racially prejudiced, and most of the commentators on his work say that these value judgments influenced his science. For example, the biologist Stephen Jay Gould argued that Morton's racism subtly influenced both his measurements and his analysis of those measurements. His belief that Europeans were superior to Africans led him to subtle errors of measurement and calculation that aligned with these prejudices. Now, it's easy to look at this case and say, here is an example of bad science. as scientists took his everyday biases and let them infect his research. In fact, Gould put it this way: "Science has long recognized the tyranny of prior preference, but the only palliations I know of are vigilance and scrutiny." In other words, Gould thinks that it's hard to avoid letting your prior values or preferences subtly influencing your work, but that the scientific community should be vigilant and subject all work to scrutiny in order to address it. Now, Gould's acknowledging the challenge to the idea that science is completely value-free, but he still holds out hope that these values or preferences can be addressed. And this has been a very common kind of response to the observation that real scientific practice seems not to be value-free. The response is that we should take the value-free ideal to literally be an ideal. It's something that we strive for. When we fall short of it, we try to do better the next time. Now, there's a lot to be said for this argument, and much of the time I find myself agreeing with it. But I want to talk about a very interesting challenge to it that comes from the work of Helen Longino. Longino is a contemporary philosopher of science and a past president of the Philosophy of Science Association, and she argues as follows: "No matter how much data scientists collect, there will always be more than one explanation compatible with what they have observed. In practice, scientists deal with this by using guiding principles such as choose the simpler explanation, or choose the one most consistent with other explanations, or choose the explanation that is tightly connected to our grand theories, like evolutionary theory or general relativity. These guiding principles are more like rules of thumb than they are like rules of logic. Their justification comes from their usefulness. They're not guaranteed to get us to the truth. Sometimes the answer does turn out to be more complicated. Sometimes other theories point us in the wrong direction, and so forth. Once we've acknowledged that these guiding principles are more rules of thumb than rules of logic, says Longino, we can see that these principles are really value judgments. Why do scientists assume that the simpler explanations are the right ones? Sure, it makes their lives easier, but when applied in the social sciences, it could lead to ignoring important differences between groups. Sometimes complex phenomena might require complicated explanations, not simple ones. Similarly, sometimes an entirely novel, unexpected explanation is the right one. So why follow a rule of thumb that says unified explanations are better than diverse ones? The reason individual scientists generally adopt these positions, Longino argues, is because they form part of a value system adopted by the scientific community as a whole. This value system explicitly prefers simpler, more unified explanations whenever possible. It says that these are better explanations because scientific theories are preferable when they're unified. Unless we knew for sure that the world was simple and unified, then this has to be a value judgment. But there's more. Since they're values, not facts, other competing values could be substituted. In some contexts, is it better to have a value system that emphasizes what is unique, what is complex, and what is disunified? And if so, when? Longino thinks that we should explicitly consider the effect that a particular set of values has on the explanations they produce. Does a preference for simplicity in sociological explanations, for example, inevitably cause scientists to miss critical differences between how we might explain men's and women's choices in the labor force? And if so, their explanations might be harming one or both of these groups by not taking the nuances of their differences into account. Ecologist and philosopher of biology Richard Levins goes even further. He once wrote, "When they encountered an unfamiliar animal in a picture book, my children would ask, 'What does it do to children?' Although philosophers go through great contortions to separate questions of reality from questions of ethics, the historical process unites them. Any theory of society has to undergo the test, what does it do to children?" So according to philosophers like Longino and biologists like Levins, even if we can state the difference between facts and values, in the actual practice of science, they are united. And this gives us room for serious value-based critique to enter the practice of science. Okay, so you might now say, sure, in practice, it's very hard to eliminate values from science, but isn't it still a good goal? If social scientists provide bad explanations because they oversimplified men's and women's experiences, isn't that just science gone wrong, not paying sufficient attention to the way the world actually is? Why do we need a different value? Why not, as a goal, no values at all, even if we often fall short of this goal? This dispute between philosophers who think that science should maintain the goal of being value-free and those that think this is an impossible or naive goal is very much a live one. Both sides acknowledge that in practice, values enter scientific judgments, but they disagree about whether this is ultimately a good thing. In the 2018 IPCC report titled Global Warming of 1.5 degrees centigrade, The authors recommended that the best way to meet the greenhouse gas reduction goals is to impose a carbon tax. In a case like this one, it's easy to see why issues of fact and issues of value are so intertwined. Scientists take themselves to be stating a simple empirical fact. The carbon tax mechanism is the one that is most likely to keep emissions down, and keeping emissions down is our only chance of meeting the global temperature goal. But for the argument to be fully persuasive, they also have to assume that everyone values keeping the global mean temperature down more than they value businesses having lower taxes. And similar assumptions have to be made throughout research that considers future climate scenarios. When there's uncertainty, should one be conservative or cautious about the future climate, or should one be optimistic? This has to come from judgments about what would be more bad or less bad in the future. We have been talking about the possibility of judgments of value, judgments of good and bad entering science. But what about the values of scientific practice itself? As with any other institution, the scientific community has certain organizing values or principles. And when people march for science, they are marching to defend these values. One interesting statement of scientific values comes from the American Association for the Advancement of Science, the AAAS as it is often called. This organization endorses what they call a statement on scientific responsibility. It reads, "Scientific freedom and scientific responsibility are essential to the advancement of human knowledge for the benefit of all. Scientific freedom is the freedom to engage in scientific inquiry, pursue and apply knowledge, and communicate openly. This freedom is inextricably linked to and must be exercised in accordance with scientific responsibility. Scientific responsibility is the duty to conduct and apply science with integrity, in the interests of humanity, in a spirit of stewardship for the environment, and with respect for human rights." Let's break this down a bit. It first defines scientific freedom, or more generally academic freedom, as the freedom to engage in inquiry and to communicate openly without restriction. This means that no one should have the authority to restrict what scientists study or how they communicate what they've learned. Now, this statement puts the freedom in pretty absolute terms, although nearly everyone would concede there are some limits. For example, researching how to build powerful explosives with household materials and publishing this information on the internet probably crosses a line. Nevertheless, the statement makes it clear that free inquiry is a central scientific value, and it ties this value to the advancement of human knowledge and the benefit of all. Philosophers often call this an Enlightenment defense of scientific inquiry. It has its origins in 18th century discussions of the liberating power of knowledge. Learning to think for ourselves and learning to learn from the empirical world are our keys to ensuring our freedom from despots, superstition, and mob rule. The second part of the statement expresses a second value. It says that scientists should be responsible with the freedoms that they have. And it's a very strong statement. It says, "Scientific responsibility is the duty to conduct and apply science with integrity, in the interest of humanity, in a spirit of stewardship for the environment, and with respect for human rights." We can think of this as the flip side of the freedom part. Since scientists should get left alone to pursue inquiry wherever it takes them, they also need to have the integrity to use science in the interests of humanity. But what does it mean to do science with integrity? Well, think about our long discussion about the failures of objectivity. Most of these cases can be traced back to scientists acting without integrity, putting their personal gain in front of the truth, or negligent conduct of some kind or other. Scientists are especially harsh punishers of fraud because they know how important integrity is to the entire enterprise. It isn't uncommon for scientists who commit fraud to lose their job and to never be able to work as a scientist again. In fact, it's the rule, rather than the exception, for them never to be able to practice science again. We could spend a lot of time talking about this particular statement, asking whether it's well justified or whether it reflects what most scientists think, but I wanted to call your attention to it for a different reason. It is unmistakably a statement of what the AAAS sees as the central scientific values. This is not about facts in the world. It's about how scientists should be treated and how they should conduct themselves. And this statement ties these value judgments to the good practice of science. I would even say that this is a political statement and shows the appropriate political position for the scientific community. Now, I want to be clear, I said political, but not partisan. This isn't about Democrats or Republicans, conservatives or progressives. This is a statement that asserts the role scientists ought to play in society and two conditions that are necessary for them to play that role: scientific freedom and scientific responsibility. Before concluding this topic, I want to return again to the March for Science and the skepticism surrounding it. As I mentioned, in a widely circulated op-ed, geologist Robert Young worried that the March for Science will serve only to reinforce the narrative from skeptical conservatives that scientists are an interest group and politicize their data, research, and findings for their own ends. My own view is that instead of worrying about what skeptical conservatives think, the scientific community should respond to them. And one way to respond to these skeptics is to argue forcefully that scientists are not politicizing their data, but they are being political by standing up for the importance of science in society. They are standing up for scientific values, the value of freedom of inquiry and the value of scientific responsibility. And I'd further argue that scientific responsibility means that scientists should tell the public what the world is like, what our place is in that world, the dangers we face, and what we can do about those dangers, regardless of whether or not we like what we find. As we near the end of the course, I wanted to take some of the more abstract discussions we've been having and talk about how this can be translated into concrete advice that anybody can use to evaluate scientific information. The most important thing I can tell you is that we should all aim to cultivate what I called a scientific skepticism, including about science itself. This means that you shouldn't trust everything you read, but you also shouldn't doubt everything you read either. The kind of fake news that circulates on social media takes advantage of our instinct to believe everything that we read, especially if what we read follows the structure of familiar sources of information, or if it confirms our preconceptions, if it tells us what we want to hear. In order to be effective, fake news requires complete trust in what we read. Such trust allowed vaccine deniers to spread the myth that vaccines cause autism. If you remain skeptical of what you read, you can be part of the solution to fake news. On the other hand, skepticism doesn't mean doubting everything. Complete doubt is the lifeblood of industry executives who want to convince you that smoking doesn't cause cancer or climate change isn't caused by human activity. In their research about these matters, Naomi Oreskes, Eric Conway, David Michaels, and others found tobacco industry executives and the public relations firms that assisted them explicitly understanding this point. One tobacco executive went so far as to write that doubt is our product, meaning that if he could get people to doubt the science that smoking causes cancer, just doubt, not even deny, it would be enough to keep people smoking. So we have to find a balance between extreme doubt and complete trust. Think about it as a healthy kind of skepticism. Be like a scientist, remain open-minded, responsive to evidence, but still skeptical. And don't just be skeptical of what you read on social media or hear from oil and tobacco executives. Be skeptical about all reporting. This isn't to say that you shouldn't trust anything written about science, but just keep in mind that something's always being left out. Some sources are undoubtedly better than others, though, so you have to ask yourself not only what you're reading, but where you're reading it. As a heuristic, you're most likely to get accurate information about science from reputable science journalism sources, Science, New Scientist, Science News, and so forth. You can also generally trust websites from EDU domains and specialist government agencies such as NASA, the National Oceanographic and Atmospheric Administration, and the Centers for Disease Control. It's also important to remember that one scientific study is never definitive. So when you read articles that summarize a single scientific study, realize that's only a sliver of the story. Here in a nutshell are the main ideas I hope you'll take away from this course. The first is that science is a diverse and complex enterprise. The story of science that your high school textbook told you, that science mainly entails successful experiments, is completely and utterly false. Scientific success unfolds in time, and the most important results often involve generations of researchers refining, revising, and pushing the boundaries. The second idea was the idea of scientific empiricism. Scientists learn about what the world is like by careful observations, experiments, and simulations. These are all publicly observable, so they can be shared, debated, and if necessary, debunked. The third idea is that objectivity comes from the community. While individual scientists try to be as objective as possible, our confidence in science, its objectivity, ultimately comes from the way that the scientific community is organized. The fourth idea is simply that scientists are human beings and that there are failures. They make mistakes, and sometimes, like the rest of us, they get completely pulled to the dark side. They can cheat and they can lie, they can sometimes get bought out. But in my experience, this is the exception to the rule, rather than the rule itself. Most scientists value truth and honesty, but even when they don't, the scientific community has set things up to self-correct and ensure objectivity in many cases. Finally, facts and values often intertwine in science. While it's an open question exactly how deeply values ought to penetrate into scientific inquiry, there is no doubt that facts and values often come together in science, especially in areas of inquiry which are of great importance to us. My overarching aim in this course has been to help you as members of the public decide how you want to engage with science as it exists today. Though we didn't have the time to dive deep into the history of science, it's worth noting that the scientific worlds that Isaac Newton or Charles Darwin lived in are very different from the world of science that contemporary researchers, like Mia Levine and Barry Medor, live in. It's worth asking whether being a scientist today demands a different outlook than being a scientist in the 18th, 19th, and perhaps even the 20th century. Science has evolved as the society that it's part of has changed, much like our Galapagos tortoises evolved when their environments changed. I think science will continue to adapt to its changing environment, and I think one of those adaptations will be increasing engagement with the public. So I hope this course will help you better engage with science and has given you a deeper appreciation of its challenges as well as its astonishing achievements.